Do you want to go ahead and get up? So I'd like to welcome you all this morning. I think I'm excited to be here to hear what more about the report that the California Council on Science and Technology did. I just want to go over a few housekeeping things. If you haven't been in this room before, the restrooms are over and to the right near the elevators, I think, on the right side. We will be having a public comment period this afternoon. If you're interested in making a public comment, please sign in with the Public Advisor's Office at the table out in front. So I'd like to welcome the members of the CCST.
Yes. Good morning, everyone. Thanks for joining us today. My name is Amber Mace. I'm the Interim Executive Director of the California Council on Science and Technology, and I'm very pleased to bring our experts here to share with you some of what we learned as we undertook this study. And I'm going to introduce it by telling you a little bit about who we are as an organization and how we perform our study process, and I'm going to hand it over to the experts. And this, you can see our names up here, and on the slide you have the slides in your possession. If you didn't get a copy of the deck of slides, they're out near the front. There's also a one-page overview of the study that lists the authors and the steering committee members as well. So this study came at the request of the Brown administration, and we received word that there was interest in understanding what we know about underground natural gas storage in the wake of the methane leak that happened in Southern California. And so we pulled a team of experts together to answer the questions for decision makers. And this is typically what we do because we were created as a nonpartisan nonprofit at the request of the legislature 30 years ago. It's our anniversary this year. And we were created to provide an independent perspective that could tap into the network of expertise that we have here in California. And we provide this impartial expertise which extends beyond the resources or perspective of any single institution. We have a board of directors and a council of experts. And this is a list of the entities that we partner with. So we have formal partnerships with the universities and national labs in California, and they provide this incredible network of expertise that come together to answer these complex issues. And in recent years, we've weighed in on a number of different topics on the impacts of hydraulic fracturing, on various aspects of the energy system, on STEM education and water, all sorts of issues. Whatever the state needs help with, hey everybody. We're brought in, and again, we bring our experts to the table. And our role is to oversee a very rigorous process. For those of you who are familiar with the National Academies of Sciences and their process, we are modeled after the National Academies of Sciences. And we convene the expertise, and we put together a balanced team to represent the perspectives and the different issue area experts that are necessary to tackle these complex issues. We address any potential conflict of interest issues in a very transparent process, and then we submit our study to an extensive and rigorous peer review process. Right, Jane? And again, this process is modeled after the National Academies to ensure that what we produce is useful and credible for decision makers. This is a scientific process, and so we take existing information. Our scientists analyze information, but they do not conduct new research. They synthesize it and then put it together through this peer review process and deliver it to the state. The report does not tell the state what to do. It tells the state what the science says, and then it's in the hands of the decision makers through their public process to come up with any type of activity or regulation based on the scientific information. And that's our goal. And so with that, I will turn it over to Dr. Jane Long, who was the co-chair of our steering committee.
Going to test my technology ability here. So I'd like to introduce the It worked. Okay. Study process a little bit. Basically, the legislation asked us to look at 3 kinds of questions. I don't know whether I'm getting feedback. Is it better if I hold it closer or farther away here? Is that better? That sounds worse. I'll try that. So after a large accident such as Aliso Canyon, it's quite natural to want to understand if the underground gas facilities that we have in the state are safe. So we were asked to look at the safety of these facilities. And then the question immediately arises, do you really need them? If they're in any way not safe, do we have to have them? What are they used for? And because people are very aware in California that we're moving towards renewable energy, the question arises in the climate policies that we have, will they obviate the need for gas storage because we won't be using as much gas? If that is the case, then do we still need it in the future? So we looked at those three questions. Basically, in a nutshell, is it safe? Do we need it? And will we need it in the future? We put together a committee to do this, a committee of experts, which is listed in this table. Jens Burkholzer and I co-chaired it. Jens is a division head at Lawrence Berkeley Laboratory. We had people who have been very experienced in the gas industry, people who understood the utility industry. We had experts in remote sensing. We had people who were experts in energy use, risk reduction, environmental regulation, environmental law. And the way this study was organized is that each of these 3 questions had a person who was in charge of collecting the information and writing a draft. And those people are listed at the end here. Kurt Oldenburg, who's going to speak after me, addressed the first question about safety. Katie Elder, who's not here with us today, was the technical expert for Chapter 2 on whether or not we need gas storage. And Jeff Greenblatt, who will speak, I'll represent Chapter 2. And then Jeff Greenblatt will talk about whether we need it in the future, given our climate regulations and laws. So the relative roles, though, of the committee that was formed and the authors is described in this slide, a little bit in this slide. Well, this actually tells you where the study authors came from. Each of the people that I mentioned were leads, but a lot of people, a cast of thousands actually, was involved in actually collecting the information and writing the report. The relative role of the committee is, I think I might have, there's not a slide on it, so I want to make sure and talk about it. The committee is a group of experts that have a broad view and a broad perspective on these kinds of issues. And they were responsible for drawing the conclusions and recommendations, and they are responsible for the executive summary of the report. The lead authors collected the information and did the analysis. And that analysis is what we would call a meta-analysis. Again, as Amber pointed out, we developed the database and interpret the database, but then the committee had to review that and approve all of the recommendations and conclusions. Notably, there are the conclusions and recommendations were consensus, and there was no dissent among the committee. There was no dissenting opinion. Had there been a dissenting opinion, we would have published it, as well as the report, but we had no dissenting opinion. The basis of, as Amber mentioned, I'll just review again, it's all peer-reviewed literature or reports, state reports, relevant publications if they're deemed to be reviewed and reliable, and then the general expertise of the committee. So we are not doing any new research. So to key question 1, focus of the talk. Kurt, you want to come on up, and I'll just introduce it while you're walking up. So what risks do California underground storage facilities pose to health, safety, and environment infrastructure? And we'll talk through that first. Yeah, come on up. Jeff, and you guys, why don't you all come up? There you go.
Can I sit here?
Yes, you may. You might want to use that. It's hard to see the screen. Oh, you can see it, right?
Yeah, I'll be using it.
Okay.
Well, good morning. I'm Kurt Oldenburg, a senior scientist at Lawrence Berkeley National Laboratory. I was the lead author of Chapter 1, which was focused on the risks posed by underground gas storage. Those are risks to health, safety, the environment, and infrastructure. Now, I was asked here to give a talk that focuses on a particular table that we included in the report. It's table 1.7-1. And that table represents a summary of the details that we got into in the rest of the chapter. So I'm going to run through quickly the results of our study, and so that's kind of trying to raise up a little bit from the level of detail, but I will get to that table because I was asked to really speak about and to that table. So again, the focus will be on the comparative risk table. So the subtopics within Chapter 1 are listed here, and they were, again, very much on the characteristics, the physical state, locations, depths, numbers of wells, amount of gas, things like that. We also looked, because we're looking at risk, we looked at the failure modes. How do these things fail? We looked at what trends might be in capacity as a system is used and as it evolves over time. We looked at human health risks. That will be the focus of Seth Shonkoff's talk later. And we looked at what contributions the leakage of methane may have on climate. And we looked at effects of the regulations, which were very much in flux, by the way, at the time of our study, in terms of those regulations being revised, what effects those regulations might have on all of this risk-related part of underground gas storage in California. So you can kind of get in a nutshell what underground gas storage is from this slide. On the left, you're seeing the 12 sites in California, the size of the circle representing the capacity of those storage facilities. There's a bunch kind of in central and northern California. There's a few in the south, and there's one kind of in the middle. On the right is a schematic, a very sketch, sort of cartoonish view of what underground gas storage is. And what you can see about it, let's see if I can get a pointer going here. What you can see about it is we have a subsurface part of the system, which comprises wells, reservoir, cap rock. And then we have, let's see, is there any freedom to, okay, let's see if this works. No. We have the wells as part of the subsurface system, and then we have the surface system. So these are gathering lines, flow lines that run across the field, compressors, expanders, processing facilities, a lot of valves, a lot of manifolds. And the way we looked at this was the wellhead is actually part of both the surface and the subsurface system. So then superimposed on underground gas storage infrastructure like you see here are the people who operate it. So there's always human and organizational factors that are relevant when we're looking at the risks and things that can go wrong with underground gas storage. So within California, there are about 400 underground gas storage or UGS wells of various ages. So that plot there on the left with all the circles, those are showing on the x-axis the date of the creation of the well, or the spud date. So you can see there are some very old wells being used dating back to the 30s and 40s. On the y-axis there is the amount of gas transferred. That's injected and withdrawn gas. And the colors correspond to the 12 different storage facilities in the state. So you can kind of see from that what fields are using older wells versus what fields are using newer wells. This is the kind of data that we then abstracted into that table that I'll get to toward the end of the talk. On the right-hand side is simply showing the injected and produced by the blue and the red color gas as a function of the month throughout the year. And overall, it's about 250 BCF or so are injected and withdrawn from all of the facilities in California. And you can see that most of the withdrawal occurs in the dead of winter, December, January timeframe, and most of the injection is occurring actually throughout the rest of the year, shown by the blue. So an individual well in an underground gas storage facility in California can be sketched by what you see here. This is called casing, the outer steel that runs down to the reservoir. Within that is what's called tubing, and there can be various stages of casing. Wells are cemented to the rock, as shown by this gray here, over various distances throughout these wells. The traditional way that underground gas storage wells were operated in California is to use the whole diameter for withdrawal and for injection. And how they did that, note, this is a packer. This separates this annular space from the reservoir, but going up through the tubing which connects it, there would be an opening like a valve, a sliding sleeve valve, or open ports. And so effectively the reservoir was connected both to the tubing, straight to the top, as well as through this annular space, or the production casing to the top. This is very non-standard for normal oil and gas wells, which actually preserve the annulus as sort of a secondary barrier in case there's a leak in the packer or a leak in the tubing. You'd have this secondary space. Underground gas storage wells formerly did not operate like this. They operated like I'm showing here, with an open valve. The new regulations ban this type of configuration. So a tubing and packer are effectively two barriers between high-pressure gas and the environment are required under the new regulations. And the well is really the focus of the containment system. If you aren't careful with your well, you can have losses. So incidents of loss of containment have historically mostly been related to wells. And this figure just shows all the different components and all the considerations that you have to make to ensure the integrity of a well. Some of the components I talked about already, the casing, the tubing, the well head. We've got cement. We've got different components. All of these have to be installed and maintained and monitored to make sure they're working as designed. And as I said, the new Dogger regulations requiring tubing and packer will greatly reduce the likelihood of well loss of containment of the type that was observed at Aliso Canyon. So that was about the wells. That's about an engineered part of the system. There's also the natural component. That is, these fields are located in various places. There are external hazards related to the locations of the UGS facilities in California. For example, there are seismic hazards, there are landslide hazards, there's flooding, there's tsunami, there's wildfire. These may be processes over which we have almost no control. Nevertheless, they can impact the infrastructure at an underground gas storage facility. There are human health hazards associated with the loss of containment. There are toxic air pollutants potentially within the gas that may be released. Exposure to humans can lead to impacts. Obviously, natural gas is flammable. It can be explosive. And so we always have that hazard when we have a loss of containment. Is the concentration high enough? Is there a source of spark? Can we actually get a fire? So there are hazards associated with the loss of gas. So the 2015 Aliso Canyon incident caused large-scale public health complaints. This is kind of a figure, a heat map as they call it, showing the frequency or density of complaints by the public for health impacts as a result of the Aliso Canyon, which is incident, which is just pinpointed here at the center. So it's considered the largest leak in U.S. history. Thousands of people were relocated, affected the health of tens of thousands of people. And as I said, Seth Shonkoff will be discussing this in much more detail. There were also, are also methane emissions, and not in a health and safety context, but in a greenhouse gas context. The release of methane is an undesirable because methane is a very powerful greenhouse gas. So it turns out, though, that these releases from underground gas storage in California are less than 10% of other sources, actually a lot less than that. So people measure these methane emissions, and we find that about 7.8%, the total UGS emissions are about 7.8% of the total natural gas-related emissions. They're only about 0.5% of total California methane emissions, and again, we have emissions from agricultural sources, from dairies and landfills. Those are larger, again, than the oil and gas-related methane emissions. And so they come to about 0.05% of the total California greenhouse gas emissions. This includes carbon dioxide and other greenhouse gases. 3 facilities currently dominate these emissions. These are measurements on Rancho, Aliso Canyon, and McDonald Island have some integrity issues that are resulting in some methane release that are being monitored. The normal emissions are roughly equivalent to having a 2015 Aliso Canyon incident every 10 years. So Aliso was significant in the context of underground gas storage. Again, relative to our total methane emissions, these are relatively small. The figure there is showing a dramatic sort of image of the way that methane emissions are measured by Steve Conley flying circular flight patterns in an airplane, measuring the concentration as he flies, the airspeed, and deriving from an equation, deriving what the net flux is that was emitted from the area encompassed by his flight path. So back to the emissions above ground, atmospheric winds and buoyancy greatly disperse leaking gases. So we did some simulations in our study, assuming a major leak was occurring, and looked at the drop-off in concentration away from the source using some assumptions about the variation in winds over the course of a day. And we see, as we knew, that the concentrations decline rapidly with distance. We know this from everyday life. Some sort of a smell emanating from the car in front of you or whatever, it dissipates very quickly. So shown in the figure is a particular case for these sorts of contours of release for some realistic winds. This is for the La Goleta site in Santa Barbara, Goleta. And you're seeing there that as you move away from the site, the concentrations drop off very quickly. So given that, flammability is mostly an on-site hazard. The concentration of methane in our atmosphere needs to be fairly high to actually have a flame. And so because of the dispersion effect, once you get very far away from a leak, it's very unlikely to have a flame or an explosion. But at the facility, it's a huge hazard. This is a flammable gas. So the leakage rates and dispersion modeling can be combined to estimate the extent of the hazard zone. That is, knowing what the lower flammability limit is, we can make an estimate. And they suggest that the edge of the red contour shown here, again, this was assuming a large Aliso Canyon scale leak was occurring through each of the wells. We would find that maybe you could have flammability within an area like this. This, again, is all up within the well field itself. The Porter Ranch area is down the hillside here. So this was a 50-ton per hour contour if you look at the red line here. And as the SS-25 well was getting toward its final bottom kill in February of 2016, it was leaking at a rate of about 20 tons per hour, so less than this. So any flammability would have been localized up to near the well pad. Okay, now I'm going to turn to focus more on this table itself. And so we called it a risk-related table. We called it various things. We never want people to look at that table and call it the risk table, okay? Because risk involves likelihood and consequences, and a few other things I'll get into. In other words, when we're looking at risk, colloquially people often are equivalencing that word with likelihood, but in fact we look at what the consequences are too. And so we combine those two to get this idea of risk. Now hazards, that's another term that we use, and we use it usually correctly in everyday life, but that's a concept of what can go wrong. It's not what does go wrong or what will go wrong, but it's what can go wrong. So keep these terms in mind as I talk here. Now, when we do risk assessment, we like to set up what we call a scenario, a failure scenario. So that's typically, or also called an accident sequence. We look at what the hazards are, and we hypothesize or envision something that could go wrong, and it's a whole sequence of events, and it has a likelihood. Typically, each of those events will have a likelihood, as well as some consequences. I'm looking at this bottle of water here. Now, as a precaution, I put the lid back on. There's a hazard, though, that this cord could knock it over. There's some likelihood of that. When it spills, I get my pages wet. That's a consequence. So that would be an accident sequence of my inadvertently knocking this bottle over. We have to put all that in when we're talking about risk. So when we look at risk, we can plot consequences on one axis from none or immeasurable to catastrophic against likelihoods. How frequent, how possible is this thing to occur? So 10 to the minus 4 per year is more frequent than 10 to the minus 6 per year. So you can start to get an idea from a figure like this that when we have a high likelihood and very high consequences, these are the things that are not acceptable. We want to avoid those. If we have lower frequencies and lower consequences, we're in a realm where something may be acceptable. So that's a Boston Squares sort of look at risk. Now, what's interesting, in Table 7.1-1, again, I'm telling you, we are not showing risk. We are showing things that are elements of a risk assessment. And what I mean by that is, when we have something like steep slopes or we have a flooding hazard, we often do a mitigation. We do something to handle that hazard. I told you I put the cap on this bottle. I've done something to put off the consequences of spilling it. So in a figure like this, where I have the consequences again and the likelihood, when I do mitigation, I'm lowering the potential impacts or the consequences, so I can move from a not acceptable to an acceptable region on this figure. Similarly, if I do something to lower the likelihood of it happening, I'm doing what's called prevention, and I can also move from the not acceptable to the acceptable. I'm going to put that bottle right there. It's less likely to be hit by my cord. So we don't include this in the table, all right? So we're including in the table kind of the hazards, we're including the characteristics that are things to keep in mind, that things are potentially problematic, but again, on a site-by-site basis, those risks can be mitigated, likelihoods can be lowered, prevention can occur. So that's the main message I want to give about Table 7.1-1. So what are we showing there? We're showing aspects of these sites that are important in risk assessment. So the rows across the top, going down the bottom, the rows are descriptive attributes. There are specific hazard categories. Their health and exposure-related aspects that Seth will talk about, and their greenhouse gas emission categories. The columns are now it's 13 underground gas storage facilities. So I've mentioned the number 12 UGS facilities, now I'm saying 13. The reason for that is we chose a period for this study to be 10 years. During that time, the Montebello facility did transfer some gas, so we had to include it as one of the facilities technically in our study period, but also technically it's been decommissioned. It's not really a storage facility at this time, but we have it in the table. So the columns are 13 facilities. There are some that are independent. There are some that are in Northern California and some that are in Southern California. The darker shadings of the table generally correspond to a larger expected hazard, but don't take that as a red flag. It just means, okay, that's something to look at. For example, it may be a darker color when there's more population nearby. On the other hand, more population nearby may mean easier access to emergency services. So there can be elements of favorability to having a large population nearby also. Those would be risk mitigation actions, and I've gone on enough about that we do not include that explicitly in this table. So I have a few blow-ups that I'll go through on the table. I know it gets very small here, but I just want to give a flavor again for what's in the table, and if there are questions about specific elements, we can talk about them in the Q&A. So again, as I've said, the facilities are along the top. These categories are along the bottom here, vertically by the rows. And we're seeing here the capacity in BCF. We're seeing here the average depth. Let's see, I think I have a blow-up of that one. Okay, so I'm just taking part of the table now. The depth of the storage reservoir, the annual gas transferred per well. This is from 2006 to 2015. We're seeing the number of open wells that are connected to the storage reservoir. We're seeing the median age of the open wells. And again, this material was covered in detail in the text of the chapter, just summarized and extracted here in the table to kind of put it together. So looking again, maybe we can see the darker greens here, darker green, and then the white. We would say that the darker greens are the things to kind of focus on. There's something there that you might want to mitigate, you might want to look at. If it's a pale color or white, it's the least of the concerns going across the various sites. Okay, similarly in the next category, which is the failure modes, the likelihoods, and the hazards. Some of the sites are on hilly areas, some of them are in flat areas, so we have differences in landslide susceptibility. These are coded by a Roman numeral that is some part of a landslide hazard formula that the California state has. The details are in the report. When we're at a facility that's out very flat, such as Gill Ranch or McDonald Island, there's no landslide hazard to speak of. Fault rupture through or within 500 meters of the flow line. So this is one where we're looking at seismic hazard maps across the state. We're looking at where faults are located, and we're seeing whether they intersect the boundaries of an underground gas storage facility and whether there are flow lines in that vicinity. Okay, this is a complicated one. The maximum 2% probability of exceeding a 0.2 second spectral acceleration within 50 years. So this is a complicated one, but these are measures of the fraction of g, the acceleration of gravity, that is occurring over this time period, 0.2 seconds. So this would be a 1.45 g seismic event, and it would have a 0.2 second time period. This would be the kind of, when it's a very low period, that would be a higher frequency. That would be something that would affect a smaller building. When it's a longer period, that would affect potentially a taller building in terms of the damage that could happen to that building. And obviously larger numbers here are worse. That's a higher acceleration. So let's see if I can go back and look broadly at the big table. Just to look at the darker colors here, we have Aliso Canyon, we've got Honor Rancho, La Goleta, and Los Medanos. These are kind of near some faults that are not expected, but they have the possibility of seismic events occurring at that frequency of that magnitude acceleration. So that's how that works. We've got let's see, another type of landslide is one that's triggered by earthquakes, and this also typically correlates with topography and how steep the site is. Tsunami hazard, this is something that's only going to be an issue for the coastal sites like La Goleta, and so that's relatively limited. Flooding hazard, we've got some sites in California like McDonald Island that are below sea level. Those have mitigated against that, by the way, but again, this is a topographic and, let's say, proximity to water related issue typically. Fire hazard, several of the sites are out in wildlands. Fire did go right through Honor Rancho recently and caused very little damage to my knowledge. Again, mitigations were in place, vegetation kept low, away from well pads, et cetera. But wildfire is a hazard to underground gas storage. This last one is the number of reported distinct loss of containment incidents. These are from some key reports by people who compile incidents or reported accidents that occur. And so this just gives you some idea of are these facilities having sort of a pattern of loss of containment, or are they having a very clean record? Okay, let's go on. This is a health and safety component. I guess this is kind of the part of the smaller version of the table. Just briefly, maybe I'll just mention a few things, but Seth may be able to go into more detail on this depending on where the discussion goes. But we did analyses of looking at the distance from where leaks could occur to populations that are nearby, and we did some analyses on what kinds of exposures just statistically there could be just based on proximity and based on the dispersion of a plume traveling above ground away from that site. Let's see. These are some of the notes. I mentioned this. The Montebello facility was officially closed December 31st, 2016. It had a long, long record of loss of containment. It was included in the table because it operated for some of the periods during our study time. In other parts of our analysis, we did not consider it relevant because, again, it's not something going forward that is part of the underground gas storage infrastructure in California going forward, and this study had a lot of forward-looking emphasis in it. Okay, there are some risk-related characteristics that are also benefits. I mentioned earlier the proximity to population may be worrisome because so many people could be hurt, but on the other hand, that's where you get your help too. Another example would be the storage volume. We coded that with a darker shade because, okay, you've got a lot there. If something goes wrong, a lot can leak, but on the other hand, there's a big benefit to having a large storage volume. That's a valuable underground gas storage facility by virtue of it having a large capacity. Finally, the new regulations require risk management. So qualitative and even quantitative risk assessment is now required under the new Department of Oil, Gas, and Geothermal Resources DOGGR regulations. And so that is something that can really change the picture of what the risk looks like at each of these sites. The table, I think, is still very relevant. It's a great place to start. What are the issues? What do we have to care about? But again, when you start doing risk management, you take care of those one by one to manage risk. So identifying, assessing, and prioritizing prevention, remember that's lowering the likelihood, and mitigation, that's lowering the potential consequences. Those actions will lead to lower risk. Now, on the area of new regulations and risk management, underground gas storage has been in kind of a gray area between oil and gas production and an energy distribution, like a pipeline infrastructure. So the new regulations are going to greatly improve underground gas storage safety and reliability. As I said, from the point of view of the well, there will no longer be a single point failure configuration allowed. That is, every time there's high pressure gas, it needs at least 2 barriers between that gas and the environment. There's extensive mechanical integrity testing. That's where you're looking at the well in various ways to ensure that over time the steel is maintaining its integrity, other components are maintaining their integrity to withhold or store high pressure gas. And then, as I said, risk management. Quantitative risk management is going to be required now. This involves risk management plans developed by each of the operators for the sites. They're site-specific. They're looking at what the issues are, and they're explaining how they're addressing them. So I guess I've said some of these things. The regulations now require quantitative risk assessment. There will be regular review and updating of the risk management plans. And they're also including an assessment of human factors. This is something that came out in our study as being critical. It's not all a physical system. There's people behind it. How are they trained? How are their shifts allocated in terms of avoiding fatigue? How is decision-making carried out? How is a handoff made between shifts? All these things need to be considered to lower the risk of loss of containment from these facilities. So the takeaway message is that risks associated with underground gas storage can be managed, they can be mitigated. The new regulations, no longer draft, are a major step. Again, improvements have been made. This is an older slide. And they should undergo regular review. That is, you shouldn't just take these regulations as from here forever, but we'll be looking at them over time. Methane monitoring for early identification of leaks is key to nip a problem in the bud before it becomes a major issue. Considering the population and proximity and population density are both important from a risk management point of view. And then information on gas composition in the case of loss of containment is really key. I think Seth will speak a lot about that. As you can see from the table, a few facilities have relatively higher apparent risk than others in California. And quantifying the risks for each facility may allow one to examine a trade-off between the benefits and the risks of individual sites. And with that, I'll close and open it up for, I don't know, do we have 5 or 10 minutes maybe?
I think you have plenty of time.
For questions. Thank you very much.
Do we have questions from the audience?
Yes. I think.
Thank you for our presentation. In your consequence chart, there's also a factor of the cost of that consequence. So I'll use your bottle analogy. You know, you cap the bottle, it's next to papers, there's a consequence of it falling down, but the cost of that consequence is fairly minor because it's just a few papers. If this was a computer keyboard, you would probably have a different perspective on that consequence.
Here's another one.
Yeah. And so the cost of that consequence must factor into assessing and quantifying that risk. And so the cost of that consequence in a field that is next to a population is significantly different than the cost of that consequence of the same likelihood, same event in a sparsely populated area. And on top of that also, there's a mention in the report that we'll talk about sometime later that the fields that are in old oil fields have a higher risk factor than fields that are just old gas field, a storage field, because of what they carry with them. And that, again, part of the cost of that consequence. And I think it's important to delineate between different fields of the same likelihood of the same event having higher cost of that consequence.
I completely agree. And
I believe that's represented in the table.
yeah, I could just say that cost of consequence, I can just put that all into the word consequence. I mean, that's, you know, however one wants to quantify it. So again, looking at the Boston Square's sort of representation, I completely agree that on a site-by-site basis, the consequences of the same type of incident may be quite different, but they would plot differently on this plot because they would vary in that measure of consequence.
So just to add, I want to emphasize here that the purpose of this table is to show that these sites are not all the same. They have different risk profiles, and they each deserve a specific risk analysis, which was not in our scope. What this table does is point to the elements of a risk analysis that you might be able to do at each of these sites.
Thank you. I wanted to ask a couple of questions.
Can you give your name and affiliation, please?
Yes, I'm Chris Parks. I'm with the California Public Utilities Commission, the Office of the Safety Advocate. I just wanted to ask on the risks specifically, did one of those also encompass subsidence?
Subsidence was mentioned in the chapter. I'm glad you brought that up. I don't think we brought it forward in the table. You might have caught it in the chapter. For others, subsidence is a fairly big issue in California due to groundwater withdrawals in many cases, but also due to basically oxidation of peat in the delta when you dry out a formerly wet area. the mass actually disappears and we get apparent subsidence. So we brought it up in the chapter, but I didn't bring it forward in the table.
Sure.
But just again, it sounds like you're very aware of it. It's a big issue. When you have a well that's anchored in the earth at 8,000 feet of depth, and it's coming up to the surface, and the ground surface, maybe the top several hundred meters, is actually subsiding, you can have some pretty significant impacts on a well. So that is something that varies across the state. Perhaps it should be brought up in the table.
Sure.
Good point.
Thank you. I was just asking. And then specifically on, I think maybe one of the last slides, you talked about regulations, room for improvement under the takeaways. Did you have anything more to kind of elaborate on those room for improvement?
Yeah, again, the slide was sort of dated. Okay. They were in flux at that time, and so many of our recommendations were taken by Dogger, not all. In the area of risk management and risk assessment, the adoption of Dogger of the requirement of doing a quantitative risk assessment was taken, and we were really happy with that. The mention of human factors, training, things like that were adopted, so we were really happy with that. One of the areas that was not taken up specifically was the issues of being very clear on gas composition in terms of understanding what the composition of gas is that could be leaking. Another one was the safety valve issue, downhole safety valves, and just what the status of those would be. So anyway, the regulations went, the elimination of the single point failure, that was the biggest one, and that solves many, many, many problems. Down in the details, there are some other things that were not completely covered, but mostly I think they did a really good job.
Any other questions? Yes.
Hi, my name is Gordon Wong with the California Public Utilities Commission, Safety Enforcement Division, Gas Safety and Reliability Branch. And I had a few questions about the dispersion model you had for the La Goleta site. I was wondering if the dispersion model shown was based on a time scale of the evolution of the dispersion, or if it was related more to the magnitude of the leakage rate.
Okay, the time scale, I mean, we do look at winds over different periods of the day. We have variability in that. Mm-hmm. The plot is, again, of this ratio of C over Q, concentration over the leakage rate. But you're asking, is it more a function of the Q or more a function of the wind? Is that the question you want to ask?
Yeah.
The model is taking both of those into effect, it's accounting for both of those, it's modeling them.
Depends on the conditions.
Yeah.
We don't know what the...
I guess if you've got, they're both factors. I can't really say easily.
Right.
I know the wind is in turbulence or big factors, big controls on diluting the dispersing gas. But I don't think there's a super simple answer to your question.
Mm-hmm. Okay.
Yeah, sorry.
I was just trying to see the extent of the model in terms of controls due to like meteorological effects.
Okay, so I can speak to that a little bit. Yes, it does have different stability classes built in. You may be aware of those, A through F. So mm-hmm. It's taking those into account. It's taking wind speed and direction into account. It is a Gaussian plume dispersion model, mm-hmm. But then we sort of abstract from that this quantity C over Q in order to put them together to make us able to just do one simulation, and then if you can tell me what the leakage rate is, I can tell you the concentration anywhere by multiplying the fraction C over Q by that leakage rate. So there's a lot of physics in the model, that's what I'll say.
Right, okay. I'll ask some more later. Thank you.
Okay.
Any more questions? Yes.
Good morning, Tom Roth, SCAPA. Question here is, does this model, or perhaps it's one that's coming up somewhere between now and the end of the day, take into consideration the consequences of not having the storage? So that at the end of the day, you'd have a net consequence.
Well, I think you're asking broadly about our study, right?
Well, I haven't gone through the whole thing.
Yeah,
I'm waiting
but I
for
think
it.
Jane or Jeff.
Well, the question is a little bit of a non sequitur because the study was asked 3 questions: to evaluate the safety of the existing facilities. Secondly, was asked, do we need the storage? And third, are we going to need this? Are we going to need this storage in the future as we implement our climate regulations? So the question that you're asking, if I understood it, do we compare the risk of having a facility to not having a facility? No, we didn't do a risk analysis, and this is not an EIS where we're comparing a project of having a project or not having a project. That's not the question we were asked. We were asked to evaluate the risk of the existing facilities.
Thank you.
My name is Saab Bagri with CPUC. My question is in regards to one of the line items you have, which is the number of reported LOC incidences as a risk factor. How readily available was the information to you that's accurate?
Two issues there. So again, we were using published data we had available. So David Evans from the British Geological Survey, Steve Folga from, not Fermi Lab, anyway, another national lab, were our sources of information. So they have published papers on this. They have been cataloging reported incidents actually from around the world. So the shortcomings of those efforts, the main one is different standards for what's reportable. And so, what you're seeing is probably a minimum, but you're seeing the larger stuff, the stuff that couldn't avoid but being reported. So I can't really vouch in the terms of accuracy, and that's why we were quite sort of didn't want to rely too much on those numbers. For people who noticed or people who will read the report, you'll notice that after more rigorous reporting was required, after the Aliso Canyon incident, when all of the sites were now reporting, the frequency of LOC incidents went way up. Okay, they were reporting more. They were reporting smaller incidents. So those data are very problematic. They're not very good for determining likelihood, in other words. So likelihood, and this is true across the field of risk assessment, it's usually the likelihood is where the big uncertainties are. It's very difficult to make predictions, especially about the future. Yogi Berra. So, I'd say we made the most of what we had available.
Any more questions? So if there are no more questions, we're scheduled to take a 15-minute break, and should we just go ahead and do that or launch the next presentation?
Maybe 10 minutes?
Okay, 10-minute break. So we'll be back here at 10:46, according to my Apple Watch. Okay, terrific. Okay, let's reconvene. It is 10:46, as advertised. Okay, so we're next going to hear from Seth Shonkoff, who will talk about the health assessment associated with question 1. Okay, we are reconvened. We are reconvened. Go ahead.
Okay, can everyone hear me? Yeah, okay. Thanks for coming, everyone. So Kurt did a really nice job of giving an overview and a lot of details of all of question 1 around risk. I'm going to go into quite a bit more detail into the actual health assessment that we undertook for this study. I'm going to start just up on the screen. These are my co-authors. Of course, I did not do this alone, and we had great effort from a variety of institutions on this health assessment. So this is the roadmap of where I'm going to take you for the next 30 or 40 minutes, just so everyone knows. And I want you to take that last bullet point and bring it to the very top. So key findings, or at least the key findings portion. I'm gonna break the punchlines first, and then I'm gonna go through how we methodically went through our assessment and came up with those findings. And then I'll end with recommendations that we came up with. Okay, so again, this is the punchline from a 150-page health assessment. I've boiled it down into 7 bullet points. So punchline number 1, there are a number of human health hazards associated with gas storage in California that are predominantly attributable to exposure to toxic air pollutants and gas-fueled fires or explosions during large loss of containment events. And with an asterisk on that it is not only large loss of containment events that emit air pollutants and other materials to the atmosphere. And I'll go through emissions reporting under the California Hotspots program of gas storage facilities during routine operations as well, in particular formaldehyde emissions from compressor stations. Number 2, large loss of containment events can cause health symptoms and impacts in nearby populations, and certainly are a key challenge for risk management efforts. Number 3, there is uncertainty with respect to some of the mechanisms of health symptoms and health impacts. So I just said in number 2, it clearly, at least in the Aliso Canyon case, clearly there were health symptoms that emerged in the population. However, the mechanisms through which those health symptoms emerged still need a bit of investigation. And I'm going to go into this a little bit more, but one of the key data gaps is uncovering what the composition of stored gas is with respect to various toxics. Gas storage facilities located in areas of high population density and in close proximity to populations are more likely to cause larger population morbidity attributable to exposures to substances emitted to the air than facilities that are further away from populations. During large loss of containment events, if emitted gases are ignited, the explosion hazard zone at certain gas storage facilities can extend beyond the geographic extent of the facility. And there are also, I'm going to go into this, there are also certain facilities where the population does not exist only outside of the facility, but is actually technically within the facility, depending on how you define the facility boundaries. Number 6, our occupational health finding. Workers on site are likely exposed to higher concentrations of toxic chemicals during both routine and off-normal operations. And workers on site have greater chance of exposure to fire explosions during loss of containment events. And that's basically a function of just being closer to emission sources, closer to areas that that have achieved the lower flammability limit. Oh, I'm sorry. There we go. Thank you. And the last one, California-specific, as well as peer-reviewed studies on gas storage in general, especially in the health, human health, population health arena, are few and far between, very thin. So we did not have a whole lot of peer-reviewed literature, especially in California, to rely on for this assessment. So I just told you our main findings from the public health assessment, and now I'm going to bring us back into how we got there. So our health assessment approach was broken up into 4 pieces. The first piece was we looked at the toxic air pollution emission data reported to the California Hotspots program. So every gas storage facility in operation in California needs to report the emissions of their toxic, what they refer to as toxic air pollutants under the hotspot program, to the regional air districts, and that information also goes oftentimes to ARB, the Air Resources Board. So we analyzed that, and I'll be talking about what we found there. We also looked at proximity of populations to and within gas storage facilities. Our proximity analysis was not an attempt to actually understand exactly what people are being exposed to and what their risk may or may not be from living far from or near these facilities, but just to start to get an understanding of the relative numbers of people that may be affected during both routine and off-normal loss of containment events. Our third component was to sort of get pretty down into the weeds on air pollution monitoring data during the Aliso Canyon SS25 well loss of containment event, and finally we did an assessment of occupational health and safety hazards. So I mentioned this briefly when I first began this presentation, but it is important to bring it up again because you're going to see this woven periodically through this presentation, and it's a really important issue. So it became clear to our public health and safety research team that in order for us to actually model and understand both the hazards and the potential risks and impacts of gas storage in general, perhaps Aliso Canyon in particular, the key there is to understand exactly what was emitted or what can be emitted. We often refer to the substance that exists in our gas storage facilities as methane. We refer to the SS25 leak, for example, as a methane leak. We chose to stay away from that language mostly because while natural gas is obviously predominantly methane, it is not only methane. And even trace substances of hazardous materials such as benzene, mercaptans, and other components, formaldehyde, can actually elicit public health and human health and symptoms and responses in the population. So as a part of this study, we did attempt a number of times to obtain relevant gas composition data, but while every operator did respond with information, none of it was really sufficient for our purposes. So that should just be known that it is still unknown, at least to us and the members of our study, as to what the composition of gas is. And I'm going to say one last thing about gas composition. So gas that is in our gas storage facilities predominantly comes from outside of California. through transmission pipelines. That gas comes in and is injected into these predominantly depleted oil fields, sometimes depleted gas reservoirs in California. And whatever the composition is of that pipeline grade gas, when it's injected downhole and in the formation, it is admixing with all sorts of constituents under high pressure and heat in the subsurface in these oil and gas reservoirs. And during withdrawal, during normal operations, that gas is sent through strippers and various glycol dehydrators, et cetera, to sort of bring that gas back to pipeline grade to send out to market. During a large loss of containment event, that cleaning, if you will, doesn't happen. And so it's the gas composition information specific to gas storage is very important to get for gas that is in these gas storage reservoirs. Okay, so going back to our assessment of toxic air pollutants under the hotspots program. So again, every gas storage facility in operation is required to report the emissions of a variety of toxic air pollutants to under the hotspots program. We gathered all those data together, and our first effort was to look at where the data was available. So as you can see, there's a table here, and maybe you can see it in the back. Everything in green is data available at CARB and South Coast Air Quality Management District. Everything in yellow is data available. Green is CARB or South Coast AQMD. Yellow is CARB and South Coast AQMD, so it's available at both agencies. Anything that's red is there was no data available. Now, we were only focused on data that was publicly available, and we didn't have the timeline or the resources to go and try to dig up perhaps data on paper at agencies. So that's the caveat. And gray is site not in operation. So we were able to get our hands on a lot of data, but not for every year and not for every facility. So what we did was, what we did for this hotspots assessment was we looked at both the types of compounds that were released as well as the reported masses of compounds that were released. And we then ranked it. So a simple multiplication between median annual emissions pounds per year of any given toxic air pollutant times the toxicity weight. And then in this order, I don't think I have a pointer, but everything is listed in order. So formaldehyde came up number 1, and that is because it is, if you can look at median annual emissions, and this is across all facilities. This is not one gas storage facility, it's across all facilities in the state of California. It is by far the pollutant that's emitted the most, and predominantly from the use of gas-fired compressors. It should also be noted that the hotspots program does not require reporting on all relevant compounds that are associated with gas storage, including, sorry, a little feedback, including things like mercaptans. captains are bad, but they're not that bad.
They don't cause feedback?
They don't cause feedback, let's just say that. Yeah.
Is the microphone working?
Okay. Are we good again?
We should be good.
Okay. Okay. Last thing I want to say on the toxicity ranking, we incorporated both acute toxicity information, chronic toxicity information when it was available, and whether or not the compound is a known human carcinogen, determined by IARC. Okay, so now I'm going to describe to you how we conducted our population proximity analysis. We evaluated population proximity near gas storage facilities, every gas storage facility in California, and as Kurt alluded to, there were 13 of them because Montebello was active for at least a certain proportion of time during our study period. We looked at total population. We also looked at children and elderly people, also other sensitive receptors such as daycare centers, hospitals, schools, and elderly care facilities. We looked from 0 meters, meaning populations living within the boundaries of a gas storage facility, and all the way out to about 5 miles, which is 8,000 meters. And then we also used meteorological data to assess dispersion patterns of where emissions might be expected to go. And I'm going to talk a little bit more about some of the limitations we had with the meteorological data available to us. Okay. So one of our findings, which was surprising, at least to us, was that there are, close to 6,000 people in California that are not living just near gas storage facilities, but actually within them. So we defined the boundaries of a gas storage facility not by individual wells, but by the aerial extent around the most at the outermost wells. The jurisdictional area of a gas storage facility is often wider than that. But from an emissions, exposure, and public health perspective, the jurisdictional boundary of facility didn't necessarily make sense, especially when assessing proximity with respect to people living between the wells in a given facility. So, a number of these facilities have, one of them has thousands of people, Playa del Rey. Montebello has about 1,470, and then it goes down from there. So we started, and if you can see this little note down here, distances were determined using concentric circular buffers. We conducted 2 different proximity analyses. One using concentric circles because, and I'll just go into this a little bit right now, the meteorological data that we had available to us, we thought that we would be able to find the nearest Met station, and that would be sufficient. In a lot of cases, however, the nearest Met station was sometimes tens of miles away, 20 plus scores of miles away, but we did the best that we could with the data we had available. So in order to not paint the picture that we were sure that the wind would never blow that way when the monitor 30 miles away said that it only blows this way, we had we first conducted sort of a broader proximity study using, again, concentric circles moving outwards. And those concentric circles had radii with distances that you can see on the left here, distance from any gas storage well in meters. And at a mile away, which is 1,600 meters, we found that there were about 114,000 people, 5,500 kids under 5, 6,300 elderly people. And then when you go out to 5 miles, those numbers obviously increase with about 1.8, 1.9 million residents. And one of the reasons why we pulled it out to 5 miles, one of the data points we used to pull it out to 5 miles is that around the 5 mile mark, at least during the Aliso Canyon SS-25 incident, in terms of the health symptoms work that the Los Angeles County Department of Public Health was undertaking in their CASPER studies, there was a pretty steep drop-off in health complaints and odor complaints at around 5 miles, although it should be noted that they did have complaints going out to a bit beyond 10 miles. But in terms of what the models are able to do, and with the data point of symptoms reporting during a large loss of containment event, that's why we had the outer bounds be 5 miles for this. So, again, as I said, we use the best available meteorological information available to be able to produce these dispersion models and dispersion figures that Kurt went into in some depth. And one of the recommendations that I'll be saying at the end that we made was that each facility should put a small meteorological, or at least wind direction station on that facility to facilitate rapid response, to be able to get people moved who are immediately downwind first, et cetera. It's just it would be a key part of risk management. And I talked about this a little bit already, but we did find that not in all gas storage facilities in California, but in some, if the emitted gases did reach the lower flammability limit or above, and were ignited, the explosion hazard zone can extend beyond the facility's boundaries. And in certain places, again, the facility boundaries are somewhat amorphous, given that people are actually living between wells in a given facility. So this is moving on to our assessment of Aliso Canyon. At the top, we provide a timeline of events during the leak, and these are just a variety of key moments that occurred, including when the leak started, when it ended, when we saw peak various air pollutant concentrations pop up on monitors throughout the extent of the leak. And on the bottom, the blue bars are, and I'm just going to get a little closer because there it is. So the blue bars are the rate of methane emissions. This is from ARB, and and take a look at the dates. This is going to be important for some of our next findings. So I really can't see. So I think about November 7th is the first bar around that time. November 28th, is that it? 28th. Yep, November 28th is the obvious peak of emissions. Looked at through emissions of methane, and then from there there's a sort of a steady drop off until. And it's not shown, but in February, after the well kill, emissions went down even more sharply. So there was a lot of monitoring, a lot of air monitoring that occurred during this 4-month period from a lot of different outfits, including state agencies, a couple of academics, SoCal Gas, and as you can see, SoCal Gas started their monitoring for 17 compounds. They were grab samples on October 30th, 2015. So a few days after the leak began, they started taking grab samples. And there was unfortunately no continuous air monitoring until after the peak of the emission from SS25. So these are some of our take-home messages from air pollution monitoring. The biggest take-home message is obviously air and environmental monitoring during this incident was very extensive, but it was still insufficient for a variety of reasons, which I'm going to talk about right now. Again, all air quality monitoring was missed, with the exception of a few grab samples, I believe from South Coast AQMD at the very, very front end. But most of the air monitoring missed the first few days of the blowout. There was no continuous health damaging air pollutant monitoring until well after the peak of emissions. So there was methane monitoring, but there was not VOC, full suite monitoring in a continuous fashion until well after the peak emission rates. Also, out of all the monitoring, only 21 compounds, which represents only 21 compounds reported as emitted from Aliso Canyon under the Hotspots program were monitored for. That represents 36% of those compounds. Compounds that were monitored for were often monitored at limits of detection above health relevant thresholds. So in particular for benzene, SoCal Gas did, again, very extensive air pollutant monitoring. But what we found when we looked at the limits of detection for benzene in particular was that about 20% of their grab samples had limits of detection that were above the Office of Environmental Health Hazard Assessments reference effect levels, or RELs, which basically gives a threshold below which, these are in very general risk assessment terms, but in general, if you're below that, there's not a whole lot to worry about, and above that, we should look harder at it for potential impacts to public health. So about a fifth, 1 in 5 samples that SoCal Gas was taking during the lead up to the peak emission had limits of detection that were above the REL. And that's important because the benzene concentrations, I don't know, I don't think anyone really knows if they were higher than the REL, but if the limit of detection is above the REL, they can say that there's no detect, even if it's above, the health benchmark defined by CaliPA and Office of Environmental Health Hazard Assessment. And so, our take-home message from looking at the air monitoring in particular during this incident was that effective health risk management requires continuous, rapid, reliable, and sensitive, defined as low detection limit environmental monitoring of chemicals of concern in both ambient and indoor environments. And to a large degree, that was achieved, but after the high intensity portion of the leak was already over. So Kurt already showed at least one of these figures. These are both from Los Angeles County Department of Public Health's assessment of reported health symptoms in the population surrounding Aliso Canyon. Spatially, it makes intuitive sense. You have the highest concentrations of complaints in the closest proximity to the well, to SS25, and it sort of dissipates as you move away. And that's basically what these two figures show. So this is also from Los Angeles County Department of Public Health. They went out and did symptom surveys in the community surrounding Aliso Canyon, and then collated their findings into tables, and this is one of them. This is verbatim, pulled out of one of their reports. So as you can see, there's a number of there were a number of commonly reported health symptoms, including eye, nose, and throat irritation, headaches and migraines, respiratory complaints, stress, dizziness, nosebleeds, etc. Now, a couple of notable issues here. One is that if you go all the way to the right, this is during the active gas leak, and this is after the well was sealed. They did two separate data collection efforts. So if you look at the last row here, weighted percent of households, about 80% of households during the active gas leak reported one or more symptoms. Now, these are self-reported data. It's absolutely the weakest form of data, or among the weakest forms of data available. But it is notable that the vast majority of households reported one or more of the symptoms up on this screen. And even after the well was sealed, still the majority of households, a bit above 60%, were still reporting health symptoms, especially upon return to their homes. So again, it appears that health symptoms are associated with at least the Aliso Canyon SS25 incident, and potentially if there was another large-scale release from another gas storage facility, we might expect similar things, but the mechanisms through which people become ill is still subject to further research. And the other thing that's very interesting from these results that we noted in our writing is there was a lot of emphasis on mercaptan exposure, because mercaptan and mercaptans are sort of the odorants that are added to gas to basically make sure that customers and people who work on pipelines know when there's a gas leak so that you can address it. There was a lot of emphasis on mercaptans exposure as the basis for why people were having symptoms, and there might be something to that. There likely is something to that. And the reason why that is posited as a potential explanation is because a lot of the symptom profiles of mercaptan exposure do replicate a lot of the symptoms that are here, but not all of them. So nosebleeds, for example, are not associated with exposure to mercaptans, yet a good proportion of those that were surveyed reported that there were nosebleeds in their households. Again, it's very difficult to say exactly what this means. Do we know what the incidence and the prevalence of nosebleeds are, during baseline? The answer is pretty much no. But people were, reporting symptoms during a specific event, and were attributing it to a certain event. So it's something to take seriously. Okay. Now, occupational health and safety. So our top line conclusion here is relatively obvious, and this is not something that's necessarily specific to gas storage facilities at all. But it's that workers are working right next to, oftentimes in closest proximity to emission sources. And because of that, they are often subject to the highest exposures to compounds that are associated with their place of work. So gas storage facilities don't seem to be an exception to that general rule. We identified that hydrogen sulfide exposure is a key concern, and this was one that that many gas storage workers said were concerns, and most people that are working in close proximity to gas were actually wearing hydrogen sulfide sensing tubes to ensure that, and other types of monitors to ensure that their exposures weren't too high in a given time-weighted average over the course of a workday. We took a trip to one gas storage facility, and so we can only speak to our findings from going to one gas storage facility right now. But we found that workers, at least some of the workers, were actually living on site in trailers. So what that means is that whatever let me back up. So occupational health exposure benchmarks are based on time-weighted averages over the course of a workday, over an 8-hour workday. So when you have people who don't leave the facility and don't leave their work site after an 8-hour workday, they are more likely to continue to be exposed to occupational related air pollutants and other compounds than those that leave their place of work. So what that basically means is that the occupational exposure values, the NIOSH's values, OSHA's values, may not be appropriate to assess the potential exposures of workers who actually stay on site day in and day out. Our recommendation is that gas storage workers may not be adequately overseen by any agency, and so it's important to note that whether a worker is an actual employee or just a contractor, that they be covered by occupational protections and regulations. So this is the table, as Kurt discussed a lot. So I won't dwell on it, but only to say that not all gas storage facilities are created equal. And there are certain gas storage facilities that have certain benefits that other gas storage facilities may or may not be offering. And there are other gas storage facilities that may have certain unique hazards that other gas storage facilities don't have. And I'm happy to answer more questions about this table during Q&A. So the key recommendations, I went through the punchlines, our findings, I went through how we arrived at those findings, and now the key recommendations from our health assessment, there's 5 of them. One is to require that composition of gas withdrawn from the storage reservoir be disclosed, along with any chemical use on site that could be leaked, intentionally released, or entrained in gas or fluids during loss of containment events. That would really help to facilitate risk analysis and risk management. Number 2, require facility-specific meteorological, i.e. wind speed and wind direction, data collection equipment, have that be installed on each gas storage facility, again, also to facilitate emergency response and other types of risk management. Number 3, require that monitoring approaches to air quality and human health be appropriately and rapidly implemented both during routine operations and during loss of containment events. Number 4, require that steps be taken to decrease exposure of nearby populations to toxic air pollutants emitted from gas storage facilities during routine operations, as well as large loss of containment events. There are a few ways to go about this. One, you can implement and enforce more emission control technologies to limit emissions that come out to begin with. And one of those key recommendations that we pulled out to the highest level, given where formaldehyde ended up on our risk ranking or our hazard ranking activity around toxic air pollution emission reporting from the Hotspots program in California, the replacement of gas-fired compressors with electric-fired compressors would greatly reduce the emissions of formaldehyde during routine and any time of operations. So we put that as a key sort of emission control recommendation. And then also think about populations and how close they are and how to think about risk in the context of, in some cases, large population centers being adjacent to and also within a lot of these facilities. And finally, require that gas storage workplaces conform to requirements of Cal OSHA and federal OSHA to protect the health and safety of all on-site workers, regardless if operators are legally bound to comply. Contractors generally do not fall under protections with these occupational agencies, and that is something to take into consideration with worker health and potential exposures. So with that, I close, and I'm looking forward to questions. Yeah.
My name is Issam Nejm. I'm a resident of Porter Ranch and president of the Porter Ranch Neighborhood Council. I have 2 questions for you. You commented that one of the recommendations was to require the disclosure of chemicals in the gas. Did considering the scientific body goes from risk to health effects and all that, was there any extension of that recommendation to set limits on different constituents of these chemicals in the gas, recognizing that you and I also take it to our stovetops and burn it, stand above it and breathe it? Was there any effort to make a recommendation towards setting limits on those constituents? That's my first question.
That's a very good question, and the answer is no, we didn't get that far. Largely because, first of all, the boundaries of this particular study was on the gas storage facility itself. So that's probably the main reason we weren't looking. I mean, to look at issues around health and safety of distribution and consumption of and transmission of gas would be a whole other assessment, an important assessment, but a whole other assessment. So I guess that's the answer.
And my second question, you mentioned the individual risks from the individual chemicals that are from the CARB and the AQMD database. Was there any at least note in the report to let the legislators or whoever is the reader of this report recognize that there's also a huge uncertainty about the compounded effect of exposure to multiple risks, and some would argue synergistic effect?
Yeah, also a very good question and point. We did certainly write about this in the text, and it's a component of our report, and it is very important to think about emissions of various air pollutants in the context of them happening either in close succession or all at the same time. And there are some models to sort of start looking at those types of synergistic and other issues associated with exposure to multiple air toxics simultaneously out of EPA and other places. So because we didn't have any real data to work with on gas composition, we weren't able, if we did have that information, we would have modeled it, we would have looked at it from, through a variety of lenses, both in terms of individual and multiple air toxics in the atmosphere at the same time. We unfortunately just couldn't get there because we didn't have that key piece of information.
Hi, good morning. Thank you for that presentation. A couple of questions.
Tim, can you introduce yourself?
Yes, Tim O'Connor from the Environmental Defense Fund. A couple of questions. One of the recommendations that the report gave and you talked about is the emissions from gas-powered compressors, and the compressor modernization project at Aliso Canyon modified some of these compressors into electric powered. But there's still, I believe, other gas powered compressors at the other facilities. I didn't see that in your chart here. Did you identify which facilities still have, at least in the SoCal Gas Network or in the other facilities, have those gas powered compressors?
Tim, that's a great question, and I don't think so.
Because some of us are commenting right now on the settlement that the state of California has proposed for the Aliso Canyon mitigation, and has asked for public comments related to that. And one could see that, of course, moving from gas-powered compressors to electric can reduce greenhouse gas emissions associated with combustion, but can also get some of these co-benefits associated with toxic pollution, toxic air contaminant discharges. And so we're looking for opportunities to provide some comments, to the state about, things else that they might be able to move forward with in terms of reducing emissions in the local air basin as well. One other question is, as part of that settlement, there is a proposed, I believe, $25 million being appropriated for a public health study. And you didn't really talk about sort of an after the fact study. Can you comment on sort of your thoughts regarding sort of how public health studies after exposure might fit into your framework regarding these health assessments? Yeah,
absolutely. So,
What'd you say? You got the question.
I got the question. We were just talking about this on the car ride over, actually. So it's clear that at this point we're a number of years past this incident. And so, some would suggest that the best thing to do with some of those funds would be to go and, conduct environmental monitoring, air monitoring, biomonitoring, looking at tissue samples, comparing Porter Ranch residents to, a control population. In my opinion, I don't think that any of that is going to be helpful at all, largely because a lot of the contaminants that we don't know what all of them were, but a lot of the contaminants that we do know were emitted are likely dissipated or broken down in the environment. And from a biomonitoring perspective, unless somebody is being acutely exposed right now, you're not going to see, say, various VOCs showing up in people's blood and urine because those are rapidly excreted. So it's kind of like, somebody saying, you got in a car accident 2 years ago, 3 years ago. We're going to we're going to give you a breathalyzer to see if you were drinking 2 or 3 years ago. That's it. It doesn't, those tools unfortunately don't work very well. So what would be left to do, there's a lot left to do, but the majority of it, in my opinion, is going to be focused on modeling and not monitoring, unless there's a reason to acutely monitor that situation, meaning are there ongoing emissions that are expected to be of high concentrations in the community or in the workplace? That very well might be the case, but you would need something like that to say one way or another whether that would be an appropriate approach. Again, the key piece of information here is what is, and in particular, what was the composition of the substance that came out of SS-25. It was mostly methane, but it was not only methane. And for example, trace substances, people talk about trace substances down to, say, 1% of a gas mixture. 1% of a gas mixture is 10,000 parts per million. So there are certain contaminants that are, for example, benzene, that are known to be chronically toxic and 8-hour exposure toxic according to Cal EPA and OEHA down to 1 part per billion. So we need to know down to the part per billion concentration what was in the gas, and then that can be plugged into various dispersion models. It can be plugged into various exposure assessments, and that's just one component. There's a variety of other things that I could talk for a long time. We should talk offline about it, but yeah, the take-home message is monitoring, unless there's a real acute reason to monitor, is probably not the best thing to do with resources to look at health impacts from 3 years ago. Modeling, gathering together information is going to be those are going to be very important tools to put into that effort.
Great, thank you very much.
Yeah.
Hi, Jean Spencer, CPUC Energy Division. So this is similar, and you've touched on this, but I just wanted to follow up a little bit. You said that all the operators provided reports on the composition, but none of them were sufficient. Mm-hmm. And I'm wondering if you could talk just a little bit more about what was lacking and what would make them sufficient for your purposes.
Sure. So just to outline the process just a little bit. So the need became clear that this information was needed. And that need was expressed to CCST, and CCST made a formal request through California Public Utilities Commission to operators, and then those responses to our request, we have an appendix that outlines both the request documents and the response documents in our study. I don't remember what the appendices numbers were, but they're in the report. So there were a few issues, and we tried a couple times. So I would say that the biggest issues came down to just lack of resolution on individual compounds. So, we got reports back that said things that, are true, which is, this is predominantly methane. True. Methane is a simple asphyxiant with no or relatively limited toxicological import. And then, ethane, pentane, et cetera. And then, on most all of the of the reports back, there were categories that said things like C6 plus. So that means anything above a compound, all compounds with more than 6 carbons on them, on their molecular structures, which includes things that are like benzene, but are not exclusive to things like benzene. There are a variety of C6 plus compounds that are relatively non-hazardous, and there's other constituents in C6 plus which are highly hazardous. And there was no way to dilate on the C6 plus percentages that they were putting in these reports to be able to say, okay, this proportion is benzene, this proportion is formaldehyde, et cetera. It's just C6 plus, which from, all of these reports would be perfectly fine from a climate perspective, and potentially from a regional air quality perspective in terms of, tropospheric ozone precursor emissions. But from a more localized perspective, it doesn't give the resolution of information down to the parts per billion concentration that are required to plug and play with dispersion modeling and exposure assessment.
In looking at the data of benzene and methane from the monitors that I've worked with, there's a clear correlation between benzene and methane levels to be able to draw some relative number to work with as predictives. Was there any attempt to work through some correlation relationships between the available data relative to methane, which was a lot of data on, to be able to delineate those levels and work with them?
It's a great question, and the answer is no. We didn't feel confident enough in being able to take those relative concentrations of both of those compounds after traveling, sometimes a mile, 2 miles, 3 miles from the source, and be able to say anything about the composition of gas, largely because benzene is not only emitted from, or during SS25, for example, which is I assume what you're referring to. Benzene is a component of most natural gas, but it's not specific to natural gas. So, it could have been next to a roadway. It could have been next to, another industry that also emits benzene. So we didn't feel comfortable taking those concentrations and those relative concentrations and saying anything about the composition to be able to plug into further modeling. So that's okay.
Any further questions? Well, hearing none, I'd suggest that we break for lunch and come back instead of at 1:15 at 1. Yeah? Okay. Yeah, 15 minutes ahead of schedule. Yes. Oh, here we go. Okay, we're going to start in talking about question 2 today, which is this afternoon. So do we actually need these facilities? And one of the things I want to emphasize in this chapter is we really looked at the problem as a whole system. We did not break apart which facilities we need or which ones we don't. But what you saw in Chapter 1 is these facilities are not all the same. So to the extent that we take some of the actions we're going to discuss here about the ways in which you could replace gas storage, it remains to do a study or an analysis of what which of these sites you might want to close. And clearly from Chapter 1, you should have seen that some of them are riskier than others. When you look at Kurt's table, you see some sites that have a lot of dark colors and some sites have light colors. And a simple-minded way of saying that some of these sites are riskier, potentially riskier than others. So I just want to emphasize again that we're looking at the system as a whole in this chapter. So please don't over-interpret what we're saying. Here. So to come to, as Seth did, we're going to cut to the chase here, and the conclusions are that the way the energy system is working in California today, we need underground gas storage. We cannot provide energy reliability in California without underground gas storage today. And furthermore, that replacing it as a whole would be extremely expensive and would also imply a commitment to natural gas that hasn't been determined in our future understanding of what the energy system might be like. So we'll walk through the analysis we did to show that, but the bottom line is that not only would it be extremely expensive, say on the order of $10 billion, but it would be very difficult to achieve by 2020, which was a date that we were actually 2030, would be very difficult to achieve in a matter of 1 or 2 decades. Then the second recommendation, or the recommendation going along with that, is that state needs to really look at the trade-offs between the risks in each facility and the benefits it provides, and the cost of replacing it. So there's a whole, if we, for example, started with the riskiest of these facilities and said, what is the cost of mitigating those risks versus what is the cost of replacing its function? And so we're recommending that the state take that into account or look at it in that manner. So here are some of the subtopics we looked at in Chapter 2. We're going to discuss some of these, but maybe not all of them today. We'll show you exactly how we think gas storage is working in the state, what some of the recent changes have been, the impacts. We looked at historical performance problems, loss of containment, to see if they actually had impacts. We found very little, so I'm not going to discuss about that today. We did a lot of work on looking at what it would take to replace the entire gas system. Again, we did not look in detail for any specific facility, but clearly there are some targets that you would want to start looking at. And we also looked at the impacts of the new regulations on reliability of gas supply. And I guess sort of cutting to the chase here is that if we continue to run the gas system the way we've been running it, there is likely the need to drill new wells, because when you produce through the annulus only, through the casing, through the borehole tubing, and not through the annulus, you essentially have less cross-sectional area. You can produce less and pump in less, so you might need more wells. Sorry for my... I just drilled my first well, and I should know all this stuff.
It was a water well.
It was a water well. So California, in a nutshell, the issue for California is how much we can produce, how much we can bring into the state and the pipeline capacity that we have versus how much we might need at a given moment or season of the year. So basically, PG&E can import about 2.9 billion cubic feet per day, and down here in Southern California, it's 3.4. We also produce some of our gas here, mostly in the San Joaquin Valley, actually, and some in the north, also in the PG&E area. And that total supply that's available at any given moment in time is 7.5 billion cubic feet per day. So that anytime you exceed that, if you don't have storage, you don't have gas. So this is what the layout of the gas pipelines look like in California. And the main thing to notice is the south is poorly connected to the north. So if you have a problem in the north and you want to rectify that in the south, or by getting gas from the south, you really only have one pipeline or one or two pipelines to do that. So we have fairly separate systems. The size of these systems, we have a bit less than a tenth of the total gas storage in California that they have in the whole country, and about 2/3 of that is in the south. Is in utilities, held by utilities, and about 1/3 of that is private. And most of the privately, independently owned ones are in the north. So why do we need it? We've identified 6 reasons for having gas storage, 6 ways that it's used. The fact of the matter is, again, the pipeline capacity is fixed at 7.5, and but as well, there can be a production issue upstream where you can't really change the rate of production. It depends on how many wells are online upstream, and you can't change that very much. Meanwhile, the demand can fluctuate below and above the amount we can bring in. And so that, in general, we're bringing gas in the summer to use in the winter. So that monthly winter demand is one of the primary reasons that we bring in, that we have gas storage, so we can meet that demand. But, and that winter demand often takes the place of a peak daily demand, and we would exceed that on a fairly regular basis. So on a fairly regular basis, if we didn't have gas storage, we would not be able to heat homes. So the demand in the winter is driven by the need for heating, not the need for electricity. And that's an important problem to keep in mind, because there's a lot of sense that if we get batteries or if we have renewable energy that we're going to not have this problem, and that's simply not the case, because the demand is driven by heat. So, or it's not obviously the case. So this direct use of gas is a very important component in the winter. In the summer, the direct use is driven by electricity for air conditioning, the peaks, so that well could be handled. But so we'll talk a little bit about that too. We also use the gas storage on a daily basis, pump in and out of storage on a daily basis to balance load in the electricity system. Gas storage has proven to be critical during extreme weather events and fires. When a facility or a pipe or a transmission line has to go down because of a fire, you can draw on gas storage to fire up someplace else and provide power. And so that is an increasingly a concern that is increasing with climate change. We also looked briefly at the financial uses for arbitrage, either seasonal arbitrage or short-term arbitrage. but we determined that these functions could be handled in another way. So they were not really a determining factor in whether we had gas storage or not. If we don't have gas storage, we could still operate the system, could still operate arbitrage. So, so we determined that the overarching reason for gas storage, the thing that determines whether or not you're going to absolutely need this or not, is the winter demand for gas. So it's the heating demand, for example, and once you have enough storage to meet that demand, you pretty much have enough storage to do all the other functions that you need. So so what we did was look at what it would take to replace the functions associated with this winter demand, and that is essentially looking at what it would take to replace all the functions. So what could replace it? We looked at pipelines to begin with, and basically we're limited by mostly by what the state can take away from the border. More gas can be delivered to the border of California than can be taken away. So we looked mostly at how to put in more pipelines inside the state, but I think as well some pipelines coming to the state would have been required. And we estimated the cost of that to be about $15 billion to meet that demand. And once you did that, it would shift the risk of not meeting demand upstream. So instead of sort of saying, gee, we got a high demand, let's just take gas out of our own storage facility here in the state, you would be asking people to send you more gas on that pipeline. So you would be subject to risks of other people wanting that gas at the same time, or production going down, or whatever would happen upstream. It would shift the risk from in-state to out-of-state. And also would, I think, significantly represent a lot of infrastructure, which would be a commitment to a way of using gas in the state that California may or may not continue to do. So we didn't, that was a pretty stiff cliff to climb to replace it this way. We also looked at LNG peak shaving units, and the price is not that much different. It's, I believe, about $10 billion, and would be extremely difficult to permit to have these peak shaving units replace gas storage. So in this case, you're basically storing the gas above ground instead of below ground. And just to say also, going back to the pipelines and this solution, they contain their own risks of leaks and loss of containment. So they're not risk-free. And one would, if you chose to go this way, you would have to carefully evaluate whether you were actually reducing risk. We looked at containerized LNG, and but these are small, and it takes 2,000 containers required to just support a 50 megawatt plant. So it would, and they take a day to recharge. So it would have huge transportation implications, and it doesn't appear to scale as a solution to scale. But let's take one of our smaller facilities, gas storage facilities in California, which may have, say, a high risk profile. This may be a very good solution for, in a limited way, to replace or lower the the demand for the function of one or two facilities, or a few facilities. We did find a small benefit from developing, from getting LNG from the Mexican terminal that's owned by Sempra, and by moving 300 million million cubic feet per day to San Diego, and then that's would be gas that San Diego didn't have to get from Los Angeles. So there was a small benefit there that could be captured. So looking carefully at this, the winter peak is, again, it's for heat, it's not for electricity. So there isn't going to be any method of conserving electricity that is going to affect this winter peak until or unless we electrify electrifying heat and providing, you'll see a little bit more from Jeff later on, but even if we electrified the heat, the amount of, the time at which you're getting that heat demand is in the winter, and in the winter, the supply of renewable energy is going way down. And so the amount of electricity storage that you would have to provide is extremely large, and you'll see a little bit more about that soon. So we think that gas storage is likely to remain a requirement for providing heat for several decades, and we need to find our way out of that. It's not going to happen by 2020 or 2030, not without spending a tremendous amount of money and also committing to a way of using gas that, having that money commit to a way of using gas that might not be in our future. So what about the summer peak? Electricity could be developed from other sources than gas. We could add some transmission, particularly for, say, Wyoming wind, which has a very high capacity factor. And we could offset about 30% of the peak gas requirements that way. It's also not an inexpensive solution, but may be important for other reasons. So to get 50 gigawatts that would be required for 100% plus emission-free supply to put on the grid would be it still would not meet the winter peak. So you could do this for the summer, but you still would not have any significant effect at all on the winter peak. So we looked at market mechanisms a little bit, and basically we found that they can help to reduce the reliance on underground gas storage, but would not eliminate the need for these services. And there's a list here of all the different mechanisms we looked at. We also found that a lot of these had already been implemented, and the gains that were supposed to be, that you could get from them, have already been gotten. It's still, all of the, again, emphasis again, a lot of these have to do with electricity. We didn't see a demand-reducing mechanism for gas in place, but that may be, for gas use, direct use, but that might be a very good place to look. So bottom line is there was no silver bullet to replace gas storage in the 2020 timeframe. There's no alternative gas supply system that would meet the needs in the winter and allow us to get this peak of 11.8 billion cubic feet per day when our input is about, our ability to bring gas in right now is about 7.5. So there were no easy solutions and no quick solutions. So takeaway messages for question 2. California needs natural gas and gas storage to meet the winter peak demand. Pipelines don't have the capacity to meet these demands. It's just a simple mass balance problem. We use more on occasion than we can bring in, and that isn't going to change very easily. It's going to be extremely expensive and not quick to do it, and nothing that we do for electricity will change that particular problem. Although it could help to lessen the need for gas storage, it won't eliminate it. And I'll take questions. Yes.
Actually, I'm curious, is the report sealed and done, or is this receiving information for that? Nice.
No, it's done. Okay. And just, can I take a second? Keep in mind that this report was started in, was it January of 2017? We nominally got the contract 2017 and went out for review 7-8 months later. So this represents work that was done over a 7 or 8 month period to collect the best information that we had, synthesize it, and draw conclusions. New information has come available since the report was written, so we're almost a year away from when it went to review. And so new information has come out, and the time period available for doing this was legislatively mandated and was extremely limited. The report is limited by that, and it's limited by what you've heard in the last 2 speakers, by the quality of the data that was available.
I appreciate that. The only reason I asked this question is you mentioned initially you set the stage to diffuse any comment about what does this mean to individual facilities. Right. And I totally appreciate that. The report is very binary in terms of yes, no, on the entire system. And you asked us not to read too much into that. But also the report could have helped by also telling the legislators not to read too much into that conclusion by stating explicitly that this finding does not negate the possibility of closing individual facilities or even the need for closing individual facilities. And it's implied, but it's not stated. And I find it to be a little shortcoming of the conclusion because it leaves an uninformed reader as saying, okay, that's it. That applies to every storage. Just a comment.
I take your comment. I wish I could rewind the clock. But just to say, though, I hope that people, particularly I think Chapter 1 is an exception to that. I laud what Kurt has done to differentiate the sites and do it in a way that's visual. I mean, you can look at that. You don't have to understand everything. You can see that some sites are potentially worse than others. And it remains to see which ones are more important than others. So I'm sorry, come on up. But I just want to make one other comment. I think it's also largely impossible it would be largely impossible for the amount of time and money that we had to differentiate the sites in terms of their function, like their utility, why we need them. We suspect, for example, that was it Playa del Rey? It's got a lot of risk associated with it. It's really small. You kind of say, well, gee, this is a good place to look for shutting one down.
And there's people living.
And there are people living nearby, so it's high risk. But we didn't really know. We didn't have information about what the utility was. So I think we could have done better in making that point clear, and in the presentations that we make, we do make it clear. And sometimes it doesn't become clear to the committee what's important until after we start to get feedback from people like you. So thanks for that feedback. Yeah.
Hello, Chris Parks from the CPUC's Office of the Safety Advocate. You mentioned there's new information that has been developed since the report was published. I was just curious, is that information being fed into any particular forums?
To us?
The new information that you have, is that information being fed into any particular forums to take that information?
I wouldn't know.
Okay.
This study is done, signed, sealed, and delivered. Committees disbanded. We don't have any funding for follow-on work.
Hi, my name is Antoine Do. I'm with the CPUC, Safety Enforcement and Safety Enforcement Division, Gas Safety and Reliability. My question is on the topic of additional pipelines as a solution to replace the UGS, right? Mm-hmm. Do you look at the physical limitation of transmitting the product through additional pipelines? Would that increase or decrease reliability, right?
Through existing pipelines?
Or existing or new pipelines, because you still have to, my understanding is you still have to push the gas through these pipelines, and the way that you can safely and reliably push the product through is at a rate very slow, like
That's
25
right.
to 30
right.
miles per hour, right? So, I mean, how does adding more pipelines would help in getting more gas more reliably from Texas to California?
Yeah, so the issue is that we did look at where it could come from, right?
Yes.
so there are several layers that you can look at for an analysis like this. One is a simple mass balance. How much do you need and how much can the pipeline carry? Another one is, and the next one, which you're referring to, also replies to any analysis that would happen that would say we're going to close this plant or reduce the functionality of another plant, or however you want to change it. You'd have to do the flow modeling, basin-wide flow modeling, to understand that you could get the gas to where it needs to be on time for various scenarios. We point to the need for that study. That's new work, that would be new research, and we didn't do it. So we agree with you, that is an issue. So our conclusion is based on the very highest level of simplest concept, right, which is that if you need 11.5 billion cubic feet per day and you can only bring in 7.5, then you need storage or some other way to get that gas. How you actually deliver that gas? A minimum would be, if you relied on pipelines, a minimum would be that you have 11.5 billion cubic feet per day of capacity. Whether you could, at that point, even make that work, we didn't go into any more detail. But we point to the need, and also it turns out to be extremely expensive to even go that far. So.
Yeah, I noticed the cost that included all the physical limitation that you need to enable to transfer all the gas, through additional pipelines?
Yeah, it was based on the capacity of the pipeline, the cost of that capacity based on recently built pipelines. So, and the length of pipeline that you would need. Whether you could actually, even having done that, whether you could actually deliver that gas to Los Angeles when you need it, or within a time frame that made sense for when you need it.
Okay, thank you. Yeah.
We didn't look at that.
Yeah, actually, Jane, if I can just add one more thing to that. It's our understanding that analysis, that $15 billion price tag, was only referring to the additional cost of bringing that extra capacity to the border or tying into the main means of distribution, but not any additional piping throughout a region that would be needed, because I believe that we basically have that capacity with the additional underground storage facilities. We can get that much gas to the different locations.
Yeah, except that one thing you said is not correct. We actually, more gas can be delivered to the state line than the state can take away. So we already have that delivery capacity to the state line. So most of that gas pipeline infrastructure was actually inside the state. And some is still required outside to bring more gas to the state line. Yeah.
Norman Peterson for the Southern California Publicly Owned Utilities. You mentioned the new information that you've gotten since you completed the study.
No, I just said there is new information. I don't have any.
Well, the study came out, at least I got my copy, and I dated it January 18th, 2018. And it would stand to reason there's new information. When you made that statement, what sorts of information do you have in mind? Or was there anything in particular that would be
I'm just saying
germane?
that the study has a time stamp on it, and whatever new understanding we have about anything. For example, there's a root cause analysis that's going to come out that could add something to Chapter 1, and we didn't have that. So it's just, I'm just trying to emphasize the fact that we collected data that was available through, I'm going to say June or July of last year. So anything that has come available, and then it had to go out for review. So really pretty much nothing that's happened in the last year is reflected in the report. That was my only point.
I see. And we, of course, are having...
We don't work on it anymore, so
yes,
we don't
I
get
understand that. Well, actually, that does tie into my next question. We are having the workshop now. You probably aren't being remunerated for your participation in the workshop. How does the workshop... What should we draw from the fact that the workshop is being held now as opposed to back closer to January 2018?
You're over my pay grade.
Okay. And just one last question. For both the tighter balancing rules And for core customers balancing to load, that happens to be a set of issues about which the utilities are very interested, because we are subject to the tighter balancing rules, but we do have the core continuing to balance to a forecast,
Right.
as you know. And it's very significant in terms of distribution of the burden of balancing. But you do note there would be small gains, and those gains are apparently in relation to reducing reliance on underground storage. Do you have a little bit better quantification of the small gains?
I don't think there was a very tight quantification of that. I think there was more of a back of the envelope kind of quantification of it in the report, but I recommend that you look more in detail into Chapter 2. I think the bottom, I think what in this report, when we got to the place where we felt like you weren't going to be able to solve the problem this way, which is the question we were asked. In other words, can we do without gas storage with tighter balancing rules? I think the answer was no, so we didn't look any farther, right? I mean, I don't think we're trying to solve every problem. It was, do we need it? Well, could tighter balancing rules obviate the need for gas storage? Answer, no. Could it make the use of that facility, reduce the use of that facility, reduce the stress on that facility? Probably yes, but we didn't quantify that.
Thank you very much.
Hi, good afternoon. Tim O'Connor from the Environmental Defense Fund. So the Public Utilities Commission in the Aliso Canyon OII and the SB 380 proceeding is developing and running a hydraulic model to evaluate a number of things, in particular about answering this question about the extent to which the use of Aliso Canyon can be reduced or otherwise eliminated. And as part of that, there's a question about whether a hydraulic model could sort of be developed that would essentially ask the question in reverse. You know, what can be done? What sort of things, should, if we did those, would we allow for the elimination of Aliso Canyon? And so, not whether, as based on conditions as they exist now, mean that we can eliminate it, but what do we need to do to be able to eliminate it? And you've sort of, the report kind of talks about that here, talks about some of those issues, or the solutions. But the answer that we get from the Public Utilities Commission is twofold. One is it's not our charge to, as part of 380 in the proceeding, to say what do we need to do to be able to eliminate it. And that there is, it's difficult to develop a hydraulic model that you can run, to get that end result. Is there any guidance that you can offer those of us that are participating in that proceeding in terms of evaluating or looking at the development of a hydraulic model based on, an outcome that we'd like to see it sort of be run to achieve, so that we can set it up at the beginning to achieve that outcome? And the second question is, there is some concern that if we don't pay attention to how the model is designed at the outset, if you just run it to say, hey, are we going to need Aliso Canyon, in the future based on a 1 in 10 or 1 in 35, scenario, that you're not actually going to be able to ask some of those questions later and then run the same model to get those results.
Yeah.
Do you have any thoughts about those?
Well,
those issues?
I think one thing is the study did commission Los Alamos to develop a hydraulic model, and they developed it, but they didn't really run it. We didn't have the time or the money, the resources to get them to do a study similar to that. I think you're right about the design of studies like that, that if you don't think about what questions you want to answer, you might not get an answer, for those questions. So I guess one piece of advice would be to talk to the people that developed the model at Los Alamos. I don't know if you're talking to them. They gave some thought to it, and we pushed them hard to talk about in the report, to talk about how the model could be used. So they did do a little bit of thinking about that. not anywhere near as much as they could. I think a critical thing for me, if I was involved in this, is linking what we know about the risk. And, again, Kurt said he had a risk-related table. So the risk, and Dogger is supposedly having each of these sites do a risk analysis. So giving them some kind of ranking, some kind of priority for which ones actually are riskier than others would seem to me to be a place to start, and then to be able to turn those off in the model and see how the system would respond, optimizing delivery where you need it, and then being able to dial in as well some demand response in gas, direct gas use, not just in electricity. So I think those are all things that you would want to have, the capacity you would want to have in the model. But I would recommend that you talk to these guys at Los Alamos, and I think Jeff might want to add to that.
Yeah, I was going to say, so we're not living in a static world. We're rapidly moving toward a higher renewable content on the grid, as well as conservation of gas in buildings, and potentially building electrification, electric vehicle charging, et cetera, as I'm sure you know. So I think depending on how far out you want to look, I think it's really important to include some of those trends, plus some variances. I'll talk about how differently the future could look in 2050, depending on which way the state or just the economics ultimately takes us.
And when you do, I know that a lot of stock is given to the California Gas Report and the projections that are sort of embedded within it, and the differences of what the future is versus what the gas report says it is. I think is going to be important for the realness of the outcome, is whether it is what the models predict or whether what something else predicts.
And there's I think one of the major conclusions that we make, and you'll hear it from Jeff, but I'll jump a little bit, is that there really isn't a coherent plan for energy in the state where all these things become integrated and we eliminate emissions. So, maybe we don't need natural gas storage, but we might well need carbon dioxide storage or hydrogen storage or some other kind of gas storage. And so the need to use part of the underground as part of the energy system that reliably meets our needs in all the integrated sectors, heat, transportation, electricity, that plan doesn't really exist. And so there's work to be done. There's just a lot of work to be done to understand how we're going to do this, and certainly a gas system model would be extremely helpful. But even standing back from that, are we going to head towards a system that, how are we going to solve certain reliability problems in a system that we have that's going to not have emissions and reliably produce energy? I don't think we've answered those questions enough to know whether we need some kind of gas storage. So I think, I think the idea of doing that kind of modeling is really important.
Thank you.
Just going to say, so the gas report looks out 10 years, I believe, and it does have some variation, but it's based mainly on weather. And I have not looked at it in detail, but I do believe that it doesn't speculate on any new policies. So it's essentially a continuation of what is already, sort of set by California policy. So there is a decrease in gas demand through the end of the decade, but
it sort of implies that the policies are achievable.
Yeah. Right.
Yes.
Yeah, we would say that the decrease that's projected is likely not in alignment with where we probably could be or where we need to be as a state in order to achieve our electrification goals and things of that nature. Yeah.
More question?
Hello, Chris Parks from the Office of the Safety Advocate of the CPUC. A couple of questions. One is, I think earlier on you mentioned the difference between the north and the south. And is there a general statement to kind of compare the situation and the need between the north and the south, or are they basically similar, or do you have any kind of general statement that you could make?
They're different.
Okay.
In a lot of different ways.
Yeah, in a lot of ways. I mean, a lot of a lot of the gas storage in the north is not run by the utilities. There are questions posed in the report about how these work, and there was some thought that you close the LISO and then you rely on the privately owned facilities to meet your gas, but they have no obligation to serve. So, there's some really interesting kind of policy and physical crossovers. There was a suggestion in the report that you should look at investment at these sites and try to understand how the utilities invest and maintain gas storage versus how the privately owned ones are operated. To just look at whether or not they're maintained up to the same standards. I think this would all be part of a risk analysis that would get done, but they're different.
Okay, thank you. And another question is, you mentioned new information. I know that this last...
I gotta rue the day. It's just an assumption. I take it back. There's nothing has happened in the last year.
I believe last winter there was a lot of concern about both having enough gas in the south for heating and also having enough gas in the south for electric generation, I believe, this last winter, which would have been more recent information. But I'm just curious if there's I'm not familiar with the details of the report, but were there any specifics that you would share about, like, there's standards for gas supply in terms of maybe the coldest day in 10 years or the coldest day in 30 years, whether those apply to home heating versus supplying electric generation? I think that those standards are different for different organizations across the country. And then also contingencies, like, okay, what is the worst case situation, whether it be considered like an N-1 contingency or an N-2 contingency of two kind of things. And I'm just wondering if, I'm not familiar with the details of the report, but I was just kind of wanting to get a better understanding of how that was factored.
So there's some tables in the report that list the demands based on 10-year and 30-year and whatnot. And I guess when I looked at it, I guess this was my impression, that the number of days that you would be called on to use gas storage in the winter wouldn't change that much whether you used a 20-year or 30-year or 90-year recurrence interval. That it didn't seem like a huge difference, that you're at the tail of that distribution, and basically just by saying, okay, well, we'll put up with a little bit more risk, would that obviate the need for gas storage? That the answer to that was no, it wouldn't. If you change it from 30 years to 20 years, you still need it.
Okay, and how about?
But I don't think we did an evaluation, for example, of all the different standards that people operate to. We just use the ones that people operate to.
Okay, thank you.
Any other questions? Okay, so if not, we'll turn this over to Jeff. Or we're supposed to have a break.
Yeah, if people need a break.
Till 2. Okay? All right, break till 2.
All right. And now for the fun part, the future. Do you want to introduce me, Jane, or should I just jump in?
This is Jeff Greenblatt.
He's amazing.
He's amazing, and he's going to give you a wonderful view of the future. He has all the new information, not me.
All right, so the third question, or part of our charge, was to ask how the implementation of climate change policy going forward and really looking out to 2050, which is as far as our climate change policies extend right now, could impact the need for underground gas storage in the future. And so we chose to look at 2 target years 2030 and 2050 to distinguish from what we were looking at in the second part, which was really kind of limited to the early 2020s or mid-2020s at most. And those are obviously important dates for state climate policy as well. So in the spirit of starting with what we conclude, so that you can you don't have to sit through the rest of it if you don't want to. So our main conclusion was that depending on the scenario, of which there could be several paths that the state might choose to follow in pursuit of its 2050 climate policy, some of them may require underground gas storage of some kind, as Jane alluded to, not necessarily natural gas storage, but it could be a different form of underground storage, hydrogen or carbon dioxide being some other important gases that might become pretty important in the future. Whereas some other scenarios may not require underground gas storage. And so we really couldn't say where it was definitely going to go. It depends, in a sense. But that we do not currently have the modeling capability to assess what these scenarios look like on the relevant timescales for both the electricity system and the gas delivery system, sufficient to answer the question of whether we need gas storage in that system or not. And so that's a significant shortcoming in terms of the analytic capability of any study that we've seen so far, and would be a necessary investment going forward. So that's the recommendation that I just stated there, that it would be very helpful to have an integrated plan and modeling to back up what these future scenarios might require in terms of underground gas storage. Okay. So the three pieces of question 3 that we had to answer were these. How might the climate policies, as well as new technology developments that we see on the horizon in this 2030 to 2050 time zone, affect the need for storage in the future? How could changes in regional grid operation or gas-electric coordination change the role of storage? And finally, taking 2050 as an endpoint, what has to change between now and 2050 in order to make these different future systems work? And so I'll talk a little bit about that at the end. So how did we answer this question? Well, because there was no new research possible given the time, budget, staffing, et cetera, what we did is we gathered information from a number of already completed, peer-reviewed, and sort of gray literature studies, 26 in all, with more than 300 scenarios represented by those studies. And I chose, as project lead, to include not just studies of the California territory, but also those that were looking at the U.S. and even a couple of global ones. And the reason I did so is California isn't that different than the U.S. as a whole in terms of its per capita energy needs, transportation, electricity mix. Obviously we're a little ahead with climate policy, and there are climate-related differences and so on, but we're still part of the United States with a lot of similarities. And so even though it's not an exact match, it provided us with some additional kind of insight, particularly because some of the U.S. studies were more detailed in certain ways, to validate that if they were seeing the same kinds of results for a U.S.-wide study as we were seeing for California studies, it kind of bolsters the conclusions. And similarly for the global studies, if they were also coming to kind of similar conclusions or not, then that might be helpful. Just a side note, it turned out that the global studies, we only collected a few, didn't turn out to be really helpful, sort of one way or the other, but we did include a couple of those because that was part of our literature review process. None of the studies, despite all this effort, really provided sufficient detail on the operation of underground gas storage in order to provide the real insight that we were looking for. And so we had to develop some estimates and approximations based on the limited information that was given to us in order to infer how a gas storage system might be operating in these various scenarios that were depicted. So again, the recommendation that we identify or develop studies that can identify these needs on all relevant timescales, ranging from less than 1 hour to seasonal level. I think you're pretty familiar by now with the major uses of natural gas, but this becomes especially important when looking out to the future where the uses of gas might change significantly. So total gas demand today is driven primarily by the use of gas for electricity, which has a summer peak associated with it when most of the gas for electricity is used, and less of the gas is used for so-called non-electricity demands, which is essentially building heating. I mean, there are other uses too, industrial activities that sort of take place more or less year-round, but it's clearly dominated by the need to heat buildings in the wintertime in California, and so that creates the winter peak, which is the larger of the two peaks, but there is sort of the secondary peak in the summer as well. And so depending on future policy, the ratio of these two demands might change. And the use of gas for electricity could be exacerbated by renewable intermittency, because we might, contrary to one might think, we may use less gas overall as more renewables are generating our electricity, but we may have to rely on them more frequently to make up for the dropouts that often occur with wind and solar. Okay, so with that stated, I'm now going to focus most of my presentation on the nearer term, 2030, and the changes that we expect to happen. It's a little easier to do this because we're only looking 12 years out, and there's a number of state forecasts as well as models that people have run, academics and so on, that come to similar conclusions about what the gas situation is going to look like by 2030. And then the latter part of the talk will be discussing the 2050 considerations. So what will change by 2030? Well, interestingly, the changes that we forecast looking across a range of scenarios that have been examined is that there won't be all that much different in the next 12 years. The main difference will be in the amount of renewable generation, which, as you know, is by state mandate going up to 50% of total demand by that year. There will, of course, be some increases in energy efficiency, increases in energy storage, which is also by mandate, demand response, growth of electric vehicles, but we determined that none of these trends by themselves would be enough to dramatically change the picture as far as how much electricity needs to be generated at different times of year, and therefore the impact of natural gas. So the main change that's happening is the renewable generation on the electricity side. And I'll show you in a moment what this figure represents. On the non-electricity side, we see uniform decreases across the various scenarios of sort of between a 10 and 20% decrease by 2030 relative to today in total gas demand. Not enough to reduce the need for underground gas storage in the winter. And in terms of temporal variation, we didn't have a lot of insight, but we suspect, again, that it's kind of in the realm of a few percent. Nothing dramatic is happening, at least by 2030, in terms of the need for gas in building heating. But you can see that there are some interesting differences here. This is a model that was run by the CEC for 2030. So it's one stochastic rendition of what the demand for gas for electricity generation might look like. This is across the entire year. And you can see that compared to 2017, which is in blue, there is an overall decrease in demand for gas, certainly, most pronounced in the spring and summer periods, where you have more generation by renewable wind and electricity and solar PV. But there are certain times where the amount of gas needed is quite similar to today. Essentially, it's still quite spiky, and there are some places where you need nearly as much gas generation as you do today. There is some amount of energy storage, by the way, in these scenarios per the mandate, but nothing dramatic compared to there's nothing more than what's modeled there. And so our conclusion is, yes, overall amount of gas is likely to decrease, but there will still be occasional needs for gas to balance the renewables that is really in the same nearly the same amount as today, at least on a short-term basis of a day or two. All right. And then looking kind of more over the entire year on a monthly average basis, this is This is now looking at the current day picture, so maybe I should have shown this first. But this is showing the breakdown between electricity for gas for electricity and gas for building heating. And so the electricity is shown with these blue bars, and the heating is shown with the gray, and the total in the orange. And so this basically shows you the difference in when the peaks occur for these two demands, and the overall kind of two-peak situation shown with the orange at top. And so it's still dominated by the winter peak. The bullets on the right, let me just go through these quickly. So total gas still peaks in the winter. Demand for gas-fired electricity peaks in the summer. I've already said that. There will be some decreases due to changes between now and 2030, but the timing of the peaks will likely remain similar to today. We're still going to need occasional generation in the summer from electricity uses of gas. However, by 2050, these could then change quite dramatically because of the other additional changes that might take place in the energy system. And I'll show you in another couple of figures what that might look like. This is just meant to kind of show, again, this 2017 versus 2030 picture for two different snapshot days to show just how different the gas demand might look in a single given day. All right, and so what we see is, so the dotted shows today essentially a simulation of 2017, and the solid lines are for a simulation of 2030. And we can see two things. One, again, the total amount of gas is going down, but the shape is, in the case of the summer in September, is changing quite abruptly, whereas it's really not changing that much in its shape at other times of the year. And here I only have two shown, summer and spring, but really everything else throughout the year is somewhere in between these two. These kind of represent extremes. And so really what we're seeing here is that it is the great increase in solar PV generation that is driving this midday decrease in the amount of gas needed in 2030 that is clearly not there today. There's a little bit of one, but the state expects it to get much deeper. And so this is great in that it's decreasing the amount of gas generation needed midday, but it also means that you have these huge ramping requirements both morning and evening, and that may actually require some increased reliance on underground gas in order to meet that faster change in flow. We can't say that because we don't have the modeling to really look at that quantitatively, but we flag that as a potential. Okay, so let me show you. Okay, so there's another issue that we highlighted in the report having to do with the challenges of increased reliance on wind and solar intermittent electricity, and that is this phenomenon that we borrowed from the Europeans and introduced in this report called Dunkelflaute, which literally means dark doldrums, times of the day or year when neither the sun is shining nor the wind is blowing, and you basically have zero renewable energy output. I have shown snapshots from actual data from CAISO in 2014. One is January, the other is June. I have not cherry-picked these. These are just sort of 3-week periods during both months that kind of show that kind of highlight the differences. And what I've circled in red are these areas that are Dunkelflaute or nearly so conditions. And you can see that there are many of them basically every evening in the wintertime, because the wintertime in California is a time when the wind does not blow very often. It's much weaker. We have much stronger winds across the state in the summertime. This is true across the state as a whole. It may not be true for wind that we import from out of state, but we don't have very much of that right now. And so in the wintertime, pretty much most nights, there's very little generation. In the summer, we have more constant wind output, as you can see by sort of this baseline being raised up, but there's still occasional periods where the wind dies down naturally, and you can experience Dunkelflaute conditions in the night times during the summer as well. And so the challenge, so who cares? Well, the challenge is that if we're relying much more on renewable electricity going forward, it means that we need to have some way of providing energy when these conditions exist. If it is simply a matter of a daily occurrence where you have to sort of make up during the nighttime, you could conceive of having enough energy storage and other technologies that would be able to shore up that gap. But the problem is sometimes this can occur over extended periods of time where there might not be enough storage. And more importantly, you can see this huge seasonal mismatch. We generate not only much less wind, but also much less solar in the winter than in the summer. And so without doing something else, we're just going to have inadequate generation during the winter months. And somehow we have to be able to supply that from some sort of a seasonal storage. And I'm going to talk about how seasonal storage is extremely expensive and difficult to execute. It's not just about building more batteries. So that's what Dunkelflaute means. So how do we combat it? Here is an example of the energy storage mandate in terms of how much power one needs to deliver from energy storage, which might be adequate. So it's this little blue bar here. And as you can see, the day to night variations, even in the wintertime, is completely overwhelms us. And this is for 2014. It's not for what we expect in 2030. And it's far less in terms of its overall capacity than what you would need to be able to do anywhere near seasonal storage. So this is really just the sort of the very beginning of the amount of energy storage that you would need. And batteries are quite expensive to build. The capacity, the largest pumped hydro facility in the state. So pumped hydro is another way of doing energy storage that is in many cases much cheaper because you have a natural reservoir and you're just moving water around instead of expensive electrochemicals. But the problem is that they're very limited sites for expansion. What we have, we've already basically built out. And even the largest capacity, is limited both in terms of duration as well as the amount of power. And so what I've put here is the largest capacity facility that we have, San Luis. And that has a capacity of about 300 hours, which is actually very unusual for a pumped hydro facility. Most of them are on the order of a 24-hour storage. And so again, the reason for putting this on here is to say, if you're going to try to do seasonal balancing using just energy storage, we're nowhere near the capacity that we need. And basically, the conclusion is that we need something else, and that something else looks very much like chemical energy storage, i.e. natural gas or some low-carbon equivalent of it. Typical battery duration project is much, much smaller than either of these two. Okay, so I just wanted to illustrate that I took that data from 2014 and I amplified it to give an impression of what the wind and solar generation might look like in 2030 and map that against the expected peak demand and sort of average demand to show yet again that even though we're generating a lot more, we're still going to have this essentially the same situation as we do today, and that battery energy storage is likely to be inadequate to deal with this problem. Okay. So I think I've already shown this. This is just another way of visualizing it. This is more of a monthly average to show that both wind and solar go through this minimum in the winter in California and have a summer peak slightly offset between wind and solar, which could be helpful as far as providing a little bit more energy in the late summer when we have an increased demand for air conditioning, but it still rolls off, and obviously every evening. If we go from using gas to heat our homes to using electricity to heat our homes, we really run up against the fundamental limitation with our renewably based electricity system, which is when we need that energy the most for heating is when both wind and solar are the lowest. And so again, we ask the question, if that's the way we're going, and it's a great way to reduce carbon emissions, what are we going to do about that imbalance between supply and demand for electricity during the winter months if we are not using some kind of stored energy? Finally, because of the intermittent nature, even at large scale, essentially most studies have shown that we need to have backup capacity. Even if it's used very rarely, we need backup capacity from gas or some other dispatchable generation source nearly equal to the total generation output of the wind and solar. And so we have that right now in terms of our fleet of existing gas generators plus what we have from underground gas storage. But it would be very difficult to be able to utilize that gas generation, even if it's biogas, if we don't have a way of storing it for quick use. Okay, so what we conclude for 2030 is intraday balancing, managing changes over a 24-hour period, could probably be addressed by various forms of demand response and energy storage, as well as imports and exports, which I didn't mention earlier, but is another way of dealing with this on a short-term basis. But the problem where really UGS seems to be necessary, at least through the next decade or so, is with these multi-day and especially the seasonal demand imbalances, as I think I highlighted. Now, I want to spend a minute, because this is really a lead-in to what happens going forward to 2050. This does not imply that we have to keep relying on natural gas, fossil natural gas. There are other gases that can be used for to provide the same service. Examples are things like biomethane, synthetic natural gas, and hydrogen that can be synthesized through various means, including water electrolysis as well as chemical. However, if we switch to those, we lower our carbon footprint, but we still have the same basic storage problem as we did before. And in addition, some of these approaches introduce a new gas, CO2, that needs to be stored. And that is likely to need additional pipelines to manage it as well, I should point out. Hydrogen also cannot necessarily just be used in the same reservoirs and pipelines that exist currently for natural gas. It has quite different chemistry and physical properties, and tends to escape from pipes that are designed to handle natural gas just fine. And so if we do move more over to hydrogen, there's going to be new challenges and expense associated with that. Not to poo-poo it, but it requires additional challenges. So basically, the amount of UGS is unlikely to change significantly by 2030. That said, 2050 could look quite different. And so now I'm going to walk you through what we developed here, which is a logic diagram to help understand the scenario proliferation that could occur. And what I'm going to walk you through are 4 basic scenarios, and I chose these 4 scenarios because this is really what the literature review revealed to us, that while there was certainly lots of little interesting variance in the many dozens of scenarios that we looked at for 2050, they all broke down essentially into one of these 4 categories that had a lot more in common than differences. And so I've oversimplified these a little bit, but I think that this serves a very useful purpose. I'm going to categorize these 4 scenarios in terms of 3 questions that the scenario essentially answers. And the first question is already shown here. How much intermittent renewables is in the scenario? Is it a lot or a little? And I know I'm being a little squishy with these words, but that's because there was not a precise cutoff. Essentially, you think of a lot as being on the order of 50% or more of your electricity is coming from intermittent renewables. If it's less than that, then we're calling it low, and it puts you into a different category. All of the scenarios that we looked at, including ones that relied very heavily on, say, nuclear power or carbon sequestration, they all had still a lot of renewables, but just not as much as the ones that were renewable heavy. That's why it's never zero. So if the answer is not very much, then the question is, okay, so what other kind of what kind of flexible generation capacity do you have then, to supplement the renewables that are there in order to provide all the energy that you need? And again, it's one of kind of 2 basic categories. Either it's largely fossil-based or non-fossil-based. And let me take another step back, because I forgot to mention this. All of these scenarios meet the 2050 greenhouse gas reduction target. So if you see the word fossil there, that doesn't mean that the emissions are going to be any higher than it is in a renewables heavy scenario. But it does mean that we are doing something actively to take care of the CO2 associated with that fossil resource, okay? So in the fossil case, what we're doing is we're putting a huge reliance on carbon capture and sequestration, CCS, in order to generate the electricity that we need, while still using a fossil energy source, which tends to be plentiful and low cost, and using existing infrastructure. In addition, in order to meet the 2050 emissions targets, there's a large amount of building electrification that has to take place to, again, further reduce the amount of fossil energy that's being used in the system where carbon capture is not available. Building electrification is a challenge to implement for obvious reasons, because we're talking about penetrating many millions of buildings with a lot of individual decision makers, and we have to do that fairly rapidly over the next couple of decades. But that aside, this is one possible future for California, not necessarily the most likely one, but one. In terms of its impact on natural gas use and underground natural gas storage, this scenario is likely to result in an increase, probably a 50% increase over today's use of natural gas or higher, and probably an overall increased reliance on UGS. So unlike some other scenarios, we'll actually need to rely on UGS more than we do today in this particular scenario. Finally, there will probably be a need for CO2 management as well, because the CO2 has to go somewhere, and some of it might be stored in state, some of it might go out of state, but we still have to manage that gas. So that's one scenario. Now, there's another one which is going to look similar in this way, but this doesn't rely on fossil energy sources for the most part, and that's what we're calling flexible non-fossil generation. And the reason we have this sort of awkward catchphrase is because it really represents a number of technologies shown on the right, all of which have some flexibility that intermittent renewables don't. Nuclear is an example at the top of the list, but also geothermal, biomass, various kinds of hydropower, as well as things like solar thermal energy with built-in energy storage that allows it to be more constant or dispatchable, as well as some other kinds of wind energy. And if we rely more on these, then we can avoid consuming fossil energy, and we don't have to do CCS and all of that. And this means that we're going to rely less on natural gas. We expect that a scenario like this would cut the usage by at least 50%, maybe more. And so we're showing 40% residual use. And this is the only scenario of the four that we expect would have an unequivocal decrease in the need for underground gas storage. We're not saying it would necessarily go away, but certainly the reliance would be reduced because we've got a more dispatchable electricity system. And we don't have all that much renewable intermittent renewables in the system as well. Plus, because of the building electrification, we're not using the gas in the winter to heat our homes. So that's another example. All right, now there's two more scenarios that I'll get to, and these both have large amounts of intermittent renewables, but they still have two quite different configurations which are important to understand. So then we come to our third question, which is, okay, a lot of intermittent renewables, fine, but how much low carbon gas is in your system? Meaning, are you still using natural gas, or are you using a substitute for natural gas like hydrogen or biomethane or synthetic natural gas, something like that? If the answer is not a lot, then we have the scenario which is probably closest to where most of us think we're going today, which is large reliance on intermittent renewables and not much biogas, because there isn't a lot of biogas available in state. In that case, in order to meet the 2050 target, we're going to have to greatly increase our building electrification, plus things we're doing on the transportation side in order to meet our climate target. But what does this mean for natural gas? Well, because of the increased reliance on intermittent renewables, we do have a decrease from today, but because of the earlier problem of balancing summer and winter and intermittency during certain periods of time, it's really not clear whether we continue to need underground gas storage or not. And so we really couldn't say unequivocally we're going to need more or less. Probably not more, but we're not absolutely sure about that. But we certainly couldn't say we won't need it anymore. And so a high renewable future does not necessarily imply that we won't need underground gas storage. Finally, there's a fourth alternative, which is we ramp up the amount of low carbon gas that we have. And in this case, we continue to use our gas system largely as we do today, but without the emissions associated with it. Whatever combination we use, it could be more hydrogen-based or it could be more carbon-based, methane-based. We're probably going to use close to the same amount of gas as we do today, because we don't have to phase it out for climate reasons. The need for UGS is, again, unclear here. If we use the gas exactly how we do today, we probably will need it. But if we have increased amounts of intermittent renewables that decrease the use for gas for certain times of year, then we might need less. But we couldn't rule it out. However, we probably are going to need storage for other kinds of gases, and I highlight hydrogen if that's there, and maybe CO2 as well, depending on how you're making these low-carbon alternatives. So it doesn't eliminate the need for gas storage in this case. So in conclusion, we have these 4 scenarios. Some of them require an increased use of gas storage. Some can allow for a decrease. Some we're really not sure without further modeling whether we need to continue to maintain our gas system or not. And none of the cases said unequivocally, we can just phase it out. There won't be any need left. Even this case still seems to suggest that we're going to need some of it, but maybe we can get away with just importing from across state lines in that case. I just highlight here hydrogen that, it's not really a big part of the state plans, but it does have some attractive features, and in some of the scenarios we looked at, it kind of substitutes for some building electrification as well as vehicle electrification. And so you could see scenarios that have a little bit more hydrogen, a little bit less electrification. But again, hydrogen might require storage in order to manage it. So our conclusions from looking at this sort of far-off view is that really the only scenario we could identify that is likely to result in a decreased reliance on underground gas storage would be this flexible non-fossil generation, which would allow enough flexibility in how we make our electricity that we might not need to rely as much on chemical energy storage, e.g. Underground gas storage. But that's not really where the state is heading right now, so it would require a policy change in order to steer us in that direction. Together with the other 3 scenarios, you can see that there are a wide variety of potential futures, and California has not made a commitment to one of them as of yet, past 2030. Some of these would require forms of gas storage, and some would not. And as I've already said, some may require more, less, or about the same amount of gas storage as today. So we recommended that California should evaluate the relative feasibility using a more detailed and robust model that can actually capture some of these effects so that we can quantitatively assess how much UGS will be needed in each of these potential futures. I don't think I need to repeat these. These are just kind of the highlights from what I just presented for you. So I think with that, yeah, time for questions.
So I have a question about the Gene Spencer with the CPUC about the Dunkelflaute situation and building electrification. Mm-hmm. And I wasn't totally clear on your scenarios how those 2 factors interact. Okay. If there was, just say that we did all building electrification and every building in California was electrified, right? Would there be enough electricity to meet the heating demand in the winter? And if so, where would it come from?
Yeah, I mean, so if this is a sort of kind of crude projection for 2030. If we maintained 50%, only 50% intermittent renewables in 2050, it would look similar. If we went to even higher levels of intermittent renewables, then you can see those red peaks just going up. But what isn't going to change fundamentally, unless we move dramatically away from solar PV and wind, onshore wind, is that we have a lot less generating capacity in the winter than in the summer. And if we go for high building electrification, that's when we're actually going to shift from being summer peaking to winter peaking in terms of our electricity demand if that happens. So we've got a big challenge ahead of us. Now, I did mention that there are a number of other low carbon / completely renewable technologies that could be used, but they're not necessarily as inexpensive or available to California as some of these others. And so I've just brought that up, Gene, so you can look at that list again. California has, at least for the time being, decided to phase out nuclear. That doesn't mean that it has to stay that way. Some of these technologies are a little uncertain in terms of how much their costs will come down and how much potential there really is. This is the subject of active work at DOE, for instance. And then, of course, there's the question of natural gas with carbon sequestration that could provide some of that and would add flexibility. I'm not advocating any of these. I'm just saying these are all technology options that could be on the table, say, post-2030.
So if I could make it a little starker, I mean, I think the point of what Jeff presented is that the answer to your question is no, there wouldn't be enough electricity if we keep going in the direction we're going.
Right.
And I think the answer is if we produce our electricity a different way, we keep in mind that the model has to be, that the electricity production has to be reliable. Dunkelflaute in the winter, at night in the winter, there's pretty much no renewable energy in California. There's no sun, categorically, and the wind dies down.
Right.
So if you don't want to heat your house in the winter, like at night, there'll be enough electricity, I guess. But, I think that basically the answer, I think what Jeff's showing is the answer to your question is not if we keep going the way we're going. But the report also lays out a whole raft of the types of resources that we're going to have to be adding to the electricity system so that the answer to your question is yes. And that, from Wyoming wind, solar thermal, wave power, nuclear power, CCS, all of these things provide the kind of resources that we're going to need to make the whole electricity system work. And I recommend a paper that's coming out that Jesse Jenkins is an author of, and they really lay out three kinds of three canonical kinds of electricity resources: those that are basically dispatchable, those that are or baseload or whatever, and you can give it a name, those that are fuel-free, and there was a third kind. I'm going to have to take a punt. But basically, he categorizes them differently than we've been categorizing, and shows that if you leave any one of them out, that the price of the electricity system also goes sky high. That the optimal for reliability and cost requires these three different kinds of resources. So the fuel-free would be your solar and wind. And then the base load kind of thing would be CCS or nuclear, or some way to produce electricity. And also I think the economics here, if SB 100 passes, I think this is a big opportunity now to look at this problem from the reliability perspective. And it's a tougher perspective. It's hard for people to really understand. You can say we want 100% renewable and everybody thinks that's good, but then that's just, not looking at reliability. So we have to bring in this reliability factor, which is really what gas storage has been about. And so doing the gas storage report gives us a window on this problem that we have to have thinking about how to integrate this whole system. And the way in which we've been analyzing it is very stovepiped. So we look at electricity and we look at, gas supply for heat, and, all these things are going to become integrated. So the grand model of energy in California, which is what Jeff was pointing to, the grand model, which has to work on timescales from the seconds to the seasons, and maybe even years, because we've got to factor in some climate change. So that grand model doesn't exist, and the grand model planning doesn't exist as a result. And so that's the fundamental reason we couldn't answer the question, are we going to need it in the future, because we don't know where we're going. And that I think is the message here. That's only a little thing.
Chris Parks, CPUC. I think you mentioned earlier, Jeffrey, about the model there not being a model for some of the different aspects of it. You mentioned also briefly the ramping, and I think maybe you were saying that maybe that part wasn't well developed or whatever. There wasn't maybe that information. I don't know if I got that right or not.
Trying to think what I said about ramping. I remember pointing to morning and evening ramps when you have a decrease in the middle of the day from solar. But what's missing, I mean, just to address what you were paraphrasing there, what's missing, we actually have we have a number of teams around the state and at places like NREL who have done hourly or sub-hourly electricity sector modeling that I think gets most things right. But what we don't have integrated with that is a similar level of time resolution and fidelity in a hydraulic gas transport model. And those two things have to work together with underground gas storage as an important component of that system in order for us to answer the question, do we need UGS or not? So the electricity system modeling capability is fairly mature, but it's the other piece that is almost completely lacking in that framework.
What I was wondering is if there's a sense for how much gas storage is being used now to get through the ramping periods, and what that trend might be, and how is it becoming a critical need for ramping? Or I'm just trying to see if I could get a better sense for like compared to a couple years ago and what might happen in the near future or the long term. Is gas storage a critical component as renewables are ramping up?
I'm not an expert in this, but I am told by the folks who helped contribute to that part of the report that there are many days during the summer, particularly during these peak summer electricity days, where we are pulling gas out of storage almost every day in order to meet the demand for electricity generation. And much of that is because of the ramping that has to happen. As we increase our reliance on solar PV, those ramps will get steeper. And so those gas turbines are going to have to work harder for short periods in order to get us through. Okay.
Thank you, Jeff. I have a number of questions. That's why I have to bring the laptop.
Okay.
My first question is, can you kind of clarify to me why do you state that non-electricity gas demand you projected out to be decreasing 11 to 30% by 2030?
That's right. I'll just bring up that graphic so we can all see that. Yeah, that's right. That's just the range that was provided by the roughly half dozen scenarios that we look at for 2030. They all show decreases, and I think the explanation for why is non-electricity gas decreasing is fairly well founded. We have had energy conservation in the state for a number of years. We're reaping the benefits of that. Meanwhile, those programs are continuing. Appliances are getting gas appliances are getting more efficient. Okay. And so everybody, including the gas industry, are predicting decreases. Yeah.
Okay, thank you for that. My second question is, what are the impacts of natural gas prices on natural gas demand?
Yeah, not something I've really looked at in detail, but I will say that, a number of these studies do look at changes in natural gas price. I mean, it's fairly, what I would say, not being completely informed about this, but I think that this is generally true, is that we are fairly inelastic. There's a small effect from having lower natural gas prices that would mean we would use a little bit more, but this is a matter of basic necessity in most cases, and so we pay higher prices for the same gas. Maybe we use slightly less gas in the winter if the prices are higher, but we still burn the gas.
Well, currently it's pretty low, right? So in the future, is it projected to be higher?
Actually, things are projected to be fairly steady or modestly increasing through 2030. But of course, these are ultimately projections by the U.S. Energy Information Administration, and they're notoriously inaccurate when it comes to the long term. So, staying up there.
And my last question is on the topic of the California wind and solar monthly output, and you showed us both seasonal kind of like curve, right, for both wind and solar.
Yeah.
So I think it's clear for wind. I'm kind of not clear on, I mean, it's clear for solar.
Solar.
You see it. But
yeah.
wind, I was kind of surprised to see that kind of follow the same seasonal trends.
I was too. It depends on what part of the country you're in. So the wind curve, this kind of monthly wind curve, is completely inverted for other parts in the country, like the Great Plains. Right. And so it does suggest that one thing we could do as a future action is to move more toward using imported wind to supplement our in-state solar generation, which would then give a somewhat of a complementarity.
Yeah, California does have imported wind, right, from Oregon and Texas.
A little bit. I'm talking about much larger amounts, and particularly from the Great Plains.
People tend to be looking at Wyoming.
Yeah,
Wyoming,
which has a very high capacity factor.
Right. So therefore, it's cheaper.
Do you know how much of wind curtailment is happening during, the fall and the winter season that could have caused the dip?
Oh no, this is no. I don't. I'd be very surprised if that even would show up here. I think that this is the real phenomenon of the wind output. I've seen this in sort of U.S. models, and they show regionally the different shapes, and it's quite distinctive. California is a little bit unique that way. Yeah.
Okay, great. Thank you.
Mm-hmm.
More questions? Okay, so I'll
wrap up.
Just trading seats, but I'll just don't bother again. I'll just
okay. Okay.
Don't bother. Okay, so basically, just to sum up. So I think just to end our session here, I think the take-home messages we'd like you to come away with are that the risks posed by underground storage can be addressed. They can be managed and mitigated. We don't think they necessarily can be eliminated, but they can certainly be managed and mitigated. And so some of the worst risks could be avoided. We see right now that you can't just wipe gas storage off the map and think you're going to be able to have a reliable energy system right now and not for the next decade or so. And furthermore, in the long-term future, we haven't got a plan that would make it clear whether or not and what kind of gas storage we're going to need in order to meet our climate goals, our 2050 goals of bringing emissions down 80% below 1990 levels. That particular goal, the plan for that is not complete enough to understand how we're going to be using the underground for gas storage of some sort, not to mention gas storage. So with that, I think we'll conclude. If there's any final questions, we're happy to take them. If not, we'll stop. We've answered all your questions. Great. Thank you very much.
I think we should thank the audience.
Yes, thank you all for being here.
Attention and excellent questions.
Thank you for sitting through it all, and Commissioner Randolph for being here with us today.
Hi, Leanne Randolph from the CPUC. Thank you all for coming and for presenting. And so we'll let you go, and then I don't know if we have any public comment. We'll check with our staff and see if anybody has signed up, but you all can try to grab your planes. So thank you very much.
Thanks, you guys. Thought it went